Robot planning and robot learning have not yet had their ImageNet moment. Learning-dominated approaches are powerful and broadly applicable, yet so far struggle to reason particularly far into the future. And by contrast, hand-designed abstractions that have been the hallmark of robot planning since its inception generalize well, yet often are limited in performance and can be sensitive to failures at the interface between perception and action. And today, we're going to be looking beyond recent progress and focusing on the challenges that lie ahead. This workshop is aimed at bringing together researchers at the intersection of planning and learning, both for perception and action, in an effort to systematize the discussion of long horizon planning and the abstractions that enable it. And with that in mind, we have a few motivating questions that you could find on our website, but that are going to guide some of our panel discussions for today. In particular, how much should be learned or hand-designed? Should agents be provided a symbolic representation of the world in advance? If learning is to be used, how can we tractably train an agent when the goodness of that agent's actions may not be apparent for hundreds or thousands of time steps or more? And where will that data come from, and in what form will it be? And finally, how can we standardize the metrics and the benchmarks and the simulators that we use to evaluate performance in long horizon planning domains? Today is going to be broken roughly into 3 panels, broken up by some spotlight talks and some poster sessions as well. We tried to roughly group people by area, but due to some time zone changes, that wasn't strictly speaking possible. But the emphasis for panel number 1 is going to be on perception. I'm going to be moderating that panel, which is going to follow immediately after this. Panel number 2 is going to focus mostly on the idea of abstraction and where these abstractions come from. And that's going to be moderated by my co-organizer, Rohan Chitnis. And then panel number 3, which is going to be after the break for conference events and lunch. So that's going to be later this afternoon in Auckland. The emphasis on that panel is going to be planning. And the moderator for that is going to be Tom Silver. And I will note that, again, due to some time zone issues, it turns out that panel number 1 is going to be almost entirely virtual, but the latter 2 panels are going to have more, in-person engagement, and the speakers are going to be here in person. So the schedule for today, you can find more on our website if you're interested in scanning that QR code. It's also available on Feedloop, which you're probably logged into. We're going to start off with the 2 panels. We're going to have spotlight talks and poster sessions after each grouping of panels. And we're going to have a Best Paper Award as well that we're going to chat about. And one thing that I want to mention as well is that, some screen went dark. Is that mixed in with the speakers today, in each one of our panels, we have a blue sky contribution that has been invited to also give a talk. So in addition to soliciting the sort of standard workshop papers and posters that are going to be presented outside, we also invited some big picture perspectives. These, people who think that there's one problem that's not being studied enough and their particular perspective on it. And so we have 3 of those. You could find the papers also on our website, and they will be giving talks about some of their recent research with an emphasis on sort of new and up and coming ideas. So the format for today, for the panel discussions, please ask your questions over Feedloop, even if you're in person. We're trying to keep things moving a little bit more quickly and make sure that we can ask sort of a diversity of questions on different topics and kind of keep the panel moving. So if you're not already logged into Feedloop, please do so. You should be able to access that through the CoRL workshop website. And we have 16 accepted papers being presented at the poster session. Each was reviewed by at least 2 reviewers, and some have also been accepted for publication elsewhere, including the main CoRL conference. And you can see our website for the links for each, and you can join us at the poster session twice today. The poster session will be the same both times, so if you can only make one, we understand, but please make sure to drop by and engage with the people who are here in person. And with that, and without further ado, despite the technical difficulties, thank you very much for, from us, the organizers. Thank you very much for CoRL for having us. And next up is going to be panel number 1. Okay. This down.
Hi, should I start? I can't really hear.
Everyone good? Everyone good? Everyone good?
Okay. Hi, should I get started?
Angel, you can start now.
Okay, thank you. So thank you for inviting me. And can everybody see my slides, my screen?
Yes.
Okay, great. So thank you all for inviting me. I'm Angel from Simon Fraser University, and I'm very happy to be here talking to you about long horizon tasking embodied AI. And so in embodied AI, what we are interested in is we're interested in having an embodied agent that can learn to perceive and act and communicate in an environment. And they may be given a goal, such as exit the bedroom and turn left down the hallway. And we wanted the agent to be able to learn how to act in order to achieve this goal. Now, so I view embodied AI, this term, as a broader term that includes not just robotics, but encourages researchers in various areas such as machine learning, vision, and NLP who are interested in studying intelligent agents and without necessarily worrying about the complexities of building a physical robot. So for us, we're quite happy in working in simulated environments. And today, I'm going to share some thoughts about how we can achieve long horizon tasks in embodied AI. So embodied AI tasks cover quite a range, including simple tasks as where we're just traveling to a goal, point goal, where we are interested in given the relative position of the goal and the distance from the agent, and we're interested in just learning to navigate to it, as well as more advanced tasks such as learning to follow language instructions or to basically do question answering in an environment where we may need to open drawers to figure out whether there is a pen inside the drawer or not, or more broadly, we've recently introduced this idea of having a meta task rearrangement, where we basically want to transform a scene from one state to another state. And this transformation can be specified in various ways, either using geometric information, so you specify for each object where you want to go, or via high-level language, and so forth. Now, so today we're interested in looking at long horizon tasks. And many common household tasks are actually long horizon tasks. Even a simple task such as watching the TV, which you may think of just as, okay, I just sit passively and watch the TV, can be considered a long horizon task in the sense that for an agent to do it, it has to be able to first go into a room where there is a TV, such as the living room, turn the TV on by first identifying the TV remote, finding it and switching it on. And then finally, after the TV is on, you want to sit on the sofa and actually start the passive part of this experience. So how would we be able to get to these long horizon tasks? So today I will share some thoughts, and I do believe in line with this workshop, modularity and abstraction are very important, and that allows us to leverage pre-trained models. And I also believe that we can leverage a lot of knowledge that is found in language. So starting with modularity and abstraction, so I will go over two examples. So I've done some work in what's called multi-object navigation. And this is a very simple task setup where it's a long horizon variant of object nav where we want to navigate to a single object that is specified by the category of the object. But now what we want to do is navigate to multiple objects in sequence. And this task basically allows us to study different approaches. And I would advocate for modular approach so we can do systematic study of different modules. So this task was first proposed in 2020, and you can learn more about it. This was originally proposed for systematic investigation of map representations. Since if you have single object nav, you may be able to get away with without having a map representation. And here, what we're interested in is also decoupling some of the more complex knowledge about the world, such as where should a sink be found. So we focus on randomly placed objects. And again, and so more recently, we've done some work where we try to do this modular approach to study how we would tackle this task. And so for this task, what we want to do is that we have an agent. He wants to go to different goals in sequence. So it will be specified as, again, as a categorical target. And then he needs to go traverse the environment and figure out, okay, that's the first goal. And then once he finds it, he'll automatically be told, you know, what's the second goal he has to go to, and then the third one, and so forth. And at each time step, you need to make a decision about whether to turn left, turn right, go forward, or issue the found command. And this, again, is a fairly simple setup, but I believe it's a kind of a practical stepping stone to some more complex tasks. And in order to tackle it, we would need these 4 different modules to be able to do perceive the environment, have some memory of where we've been, potentially with explicit map, as well as do exploration and navigation. So again, the setup is that the agent has access to egocentric view of the environment, color, RGB and depth, as well as the pose, and he's given at each time step what the next goal should be. Again, we're doing simple cylinders, colored cylinders, so the goal can be expressed as, okay, you want to go to the yellow cylinder. And then so the different modules we would want is to have an object detection module to identify, have we located can we see the objects of interest in this current frame? And then also to take the information from each frame and then use that to build a semantic map of the different goals, potential goals we have seen. And with this map, then we can very easily match it against our goal to be able to say, okay, this is where we have seen the goal, on the map, we know where it is, and that's where we want to go. Sometimes you may, but at the beginning, our map is incomplete, and we may need to do some exploration to figure out where to go. So we also need an exploration policy to help us build the map. And with this, and the exploration policy will pick a relative point again about where to go next. And this together will then form a navigation goal target that the agent can go to. And the agent can then, using that, to figure out the low-level actions that it needs to do. So again, the idea of a modular approach is that we can then systematically study each component. And it's actually very nice if we can pre-train each module, but it's even better if we can fine-tune the system more end-to-end. So for pre-trained models, this is fairly standard, the use of pre-trained vision backbones, but we can also consider using pre-trained models for other components as well. So if we look at our modular framework, it's fairly standard to use a pre-trained, say, faster RCN for object detection. For the exploration policy, we can also have a pre-trained model that figures out where to go next. We actually find that even using random exploration can work pretty well. The other component which we can use a pre-trained model is this navigation agent, where we can use a pre-trained point nav agent, since we now have encodings of where we want to go relative to the agent, that can basically is already trained to be able to just figure out the set of actions that it wants to go. And with this approach, we find that using a pre-trained point nav model works pretty well. So we did some experiments with, this experiments are with semantic segmentation, that's like Oracle semantic segmentation. And you can see it can work very well using this pre-trained point nav agent. And versus if you have a task planner, that's this is a breadth-first task planner, there may be gaps where it is not able to find a proper path, or there may be gaps between the path it finds and the set of actions that the agent can actually take. So using a pre-trained model there is pretty good. The other example I want to talk about is this idea of doing rearrangement. So this is part of a large effort published at last year at New Rips. And in here, the idea is that we want to rearrange objects so that they are in a good position. And the specification is currently in geometric specification, goal specification, in the sense you are given the 3D coordinates of the initial position and the target position of the object. Again, this is a large collaboration, and the objects are randomly placed and need to be arranged. So the agent needs to be able to do a series of steps to navigate to an object, pick up an object, go to the receptacle and repeat this, place it, and then repeat it several times. And to make it easier, what we have is that all placements are on open surfaces, so not on indoors. And the agent has access at each time step to a camera that's on the arm and on the head as well. And it will then figure out how to, and in addition, we don't worry about the actual act of grouping, so we use a magnetic grouper. And we investigate different approaches that are modular, as well as end-to-end approaches. So the one approach that's proposed in the paper is this task planning plus a set of basic skills that are learned via RL. The skills would be to do pick, place, and open and close. And these skills can be composed together. And this is compared against our end-to-end monolithic RL policy, and this is just the task planning skills RL, as well as a more traditional task planning and plus sense plan act approach. And for that approach, it's actually very sensitive to the to where things are. So we actually also have a privileged version of it, where we give the ground truth of the scene geometry, as well as use a perfect controller that can set the arm exactly. But so what we see here is that when we compare these different agents, the performance goes down over time. And we also see that for this, so the faded lines are the ones with the oracle, where it has an oracle navigation. So what you see here is that if there's errors that can be compounded, and we see that the task planning plus the skills-based RL works the best. So yeah, so here's just a picture of it going, and sorry, yeah, and yeah, okay, so we'll move on. And one of the main issues is that if there's handoff problems, so that basically what happens is sometimes if you if the agent navigates to a point that's not close enough, it's not able to place the target or pick up the target. And there's more recent work that improves over this, where basically it allows for even when you're placing, to move the base a bit so that the navigation and the manipulation is not completely decoupled. So we advocate a modular approach, but even with a modular approach, there are some challenges. One of the keys is identifying what are the appropriate abstractions, what are the low-level skills we want, and what should be the API. So like we have some separate projects where we believe that, you know, we can maybe potentially decouple the vision problem, perception problem from some of this learning what to do. And so if we wanted to open doors and stuff, maybe it's useful to be able to identify what parts of the object can open and what state they're in. But it is an open question of what should be these abstractions and whether can we even learn what these abstractions are, as well as, you know, for general task planning, even once we have the skills, how would we chain them together and how can we handle that variety of tasks, the different tasks. So to do that, I believe we should leverage language and large language models. And using language for task specification, I think, is an important future direction. So this is not some work I've done, but other people have noticed that the large language models can be a source of knowledge, and you can use these models as a bridge with language specification, either for perception, where you basically use these large language models to basically detect objects that maybe with open vocabulary, or for embodied AI as well. Or you can actually even do planning with these large language models, like with ChatGPT. You can ask it, how would you set a table for 4, and it would give you information about what things you need to get and how to place them. And again, this is other people have done exciting work on this about, you know, so you can they can do planning where you have a task like brushing the teeth, and it'll tell you, the language model can tell you what are the steps you need to do to brush teeth. You can also couple these language models with perception so that it can tell you things that you may want to do. For instance, you know, maybe you want to clean up something that you currently don't have, you know, what do you have in the environment to help you clean up? And people also have done work with code as policy. This is not my work, but I think this is a very exciting direction. As a summary, I think we should aim for modularity, use pre-trained models, and use language as a bridge, because language allows for us to communicate with the robot, as well as a good source of knowledge.
All right, let's thank our speaker. Great, thanks everybody. We're going to hold questions until the end. Feel free to type them in the chat, but we're not going to directly address the questions until the panel discussion. So please get those ready. But first off, I have a quick announcement. Apparently, Rao is not going to be able to make this first panel discussion. I hope everything is well, but he, very last minute, he's not going to be able to make it. So we still have 2 more exciting speakers to look forward to. So next up is going to be Laura Pinto from New York University. Is he in the chat, in the Zoom?
Yep, I'm on Zoom. 1 second.
Feel free to share your screen. Rohan, is he there? Great. Okay, excellent. Yeah.
Are you able to see my screen?
We can hear you, but I think it's just, yep, perfect. All right, feel free to get started.
All right. Thank you, Greg, for the nice and warm introduction. I'm really excited to be here, although I would have loved to be there in person in Auckland. So today I'll be talking about how can we create or build large robot models. I think it's a nice sequencing from Angel's talk, where she sort of ended with sort of looking at large robot models. And sort of just starting from there, right? We have seen in the last few weeks, especially, that large models are now about to take the world by storm, right? We have seen things like OpenAI's model, where if you feed in some amount of text, it can output really coherent answers. In fact, I recently asked it what are the biggest challenges in robotics, and the answer it gives is actually at the level of a expert roboticist. It's not just in language. We also have models in vision as well, where it can create, or these models can create images that look extremely realistic. But if you look at them closely, they're clearly not a real world object. So we have large models that are doing well in language, doing well in vision. So let's see how do these models actually work. So from a bird's eye view, there are two main ingredients to make a large model work. The first ingredient is that you need to have large amounts of human generated data. Why human generated? That's because we want our data to be high quality, right? So if a human uploads some amount of text on the internet, it's usually a coherent sentence, or at least I'm hoping that most of the text we upload is a coherent, is something meaningful and interesting. In the same way, when we upload images, for instance, we don't upload images of the ceiling or of the carpet. We upload images of things that we think are interesting. So this sort of interesting, high quality data is really important to train these sorts of large models. Now, apart from this high quality data, we also need deep networks. We need deep models, high capacity models that can sort of absorb this data and learn from this data, right? So in language, we have models like a transformer. In vision, we now have models like a diffusion network, right? And so we have all of this interesting work in large models for language and for vision. So the obvious question is, why not in robotics? Why don't we just take the same story of large models, take these same ingredients, and just apply it on a robot? Well, now sort of obvious thing in robotics is that both of these ingredients don't actually exist in robotics yet. So if you look at high quality data, there is nowhere on the internet where I can just go and download high quality human generated robot experience for the robot I have in my lab, right? So I don't have any of those examples. And then on the other side, most of the deep networks which you're seeing nowadays have been created for vision or language. But vision and language is not the same as a robotics problem. In robotics, we need a robot to apply a continuous action in the world, physically interact with it, and make things happen, right? So the sort of models which we have created, they don't work immediately onto a robotics problem. So in this talk, what I'm going to do is to present two ideas. One, in terms of how we can get high quality human data, and the second one on how we can sort of use existing knowledge of deep networks and translate it onto robotics. All right, so with that, let's get started. Let's look at how we can get high quality experience or data on the robot. So I'm going to start with one of the most complex manipulation problems, that is a robot hand. So this is our four-fingered Allegro hand. It has 16 degrees of freedom. And let's say I want to get high quality experience on this hand. How would I go about this? Now, one straightforward option is you can use something like a cyber glove, where if you move it, the robot can follow those movements, and you can use it to create some interesting data. The issue with this is that if you have used it, you would have noticed that it's actually quite expensive if you want to buy it. And every time you use it, you need to pre-calibrate it for the human hand, right? So it's not really scalable if I want to create large amounts of data. On the other side of the spectrum of the cost, we can look at just take single images of a human hand, do hand pose estimation, and then ask the robot to follow those hand poses. So this is a technique which we have looked at in the past, but over here, the sort of issue is that the outputs from a single camera hand pose estimator is often too inaccurate, right? It's because from a single view, there's a lot of occlusions. You don't have a clear estimation of depth. And so it's often hard to get this to work. So it seems like we want a middle ground over here, where we want to get accurate estimates of the hand, and we also want it to be cheap. So how do we do this? Now, fortunately for us, it's not just us as roboticists who want to get high quality estimates of hands. Facebook and Mark Zuckerberg are also very interested in this problem. It's a key idea if you want to create a metaverse, you want to understand how human hands work. And so we saw that the Oculus VR headset is actually a really good tool to sort of immerse humans along with being able to get accurate hand poses. So we created a framework which is called HoloDex, and the framework works as follows. We have a human operator, which you can see on the left-hand side here. They are wearing this this Oculus headset. And in the Oculus headset, what they see is a sort of virtual environment or a mixed reality environment where they can see the robot along with their hand. Now, as they move their hand, we get really accurate hand pose estimates and translate those hand pose estimates onto the robot hand. So through this process, this human operator, they're able to do real-time control of this hand just using a $300 headset, right? So it's really cheap, really accurate, and also it's at real time. Okay, so what can we actually do using this framework? Well, let's try to train some models over here. So to train some models, first thing we need to do is to get a bunch of data. So we look at 6 different tasks. Oops. So okay, not sure why these videos are not playing, but there are 6 different tasks over here. The first 3 tasks are quite simple. They involve in-hand cube rotation, and the last 3 tasks are sort of more involved. They include opening a bottle and doing some sliding and picking tasks for really slender objects. So across the board, what we see is that if you use this holodex framework in mixed reality, we find that you can get about a 2x speed up in data collection for easy tasks. And for the hard tasks, we find that it's the only framework which can so it's like you're not able to use single image frameworks for the hard tasks. Only this holodex framework is able to solve it at the price point of $300. All right. So after this process, what we do is we want to now learn a policy. In our case, we try to learn a vision policy over here because we want these models to translate across objects. So to do this, first of all, we take all of our images, all of our visual data, and do self-supervised learning to train an encoder, right? So this encoder is basically, you can view it as some sort of a neural network model that takes high dimensional images and makes it into a low dimensional feature vector. So this thing is done in an offline manner. And once you have an encoder, you can now immediately run a policy on the robot. So what we do is during the rollout our rollout time, if we have an image of the robot hand, for example, an image of this sort, we first encode this image into something low dimensional. So a low dimensional encoding from the encoder. And after this point, we just do nearest neighbor matching on the demonstration set. So we look at all the examples in the demonstration set, find the nearest neighbor match, and simply just apply that action on this robot. Right, so this is a very simple strategy. Even an undergrad who's just learning about machine learning should be able to code this up. And it actually works quite well. So here on the left-hand side, I'm showing you a policy rollout on the training object, right? So over here is doing a planar rotation in-hand manipulation for this object. But interestingly, since this is a visual policy, we can just change this object. We can replace this cube with any of the other objects on the right side. And this policy immediately works on these objects, right? So we get some sort of like a zero-shot translation from training objects to a testing object. And it's not just true on the planar rotation case. We can do this on the object flipping case, where over here is trying to do out of plane rotation. And again, on the right side, you'll see that the same policy works on objects that were never seen during the training time. Here is the case of the can spinning. Again, on the left-hand side, we train it on the Pringles can. And on the right-hand side, you see that the same policy also works on these new slender objects that were never seen in training. Okay, so if you're interested in this, all of our code, we also created an app to use on this VR headset. So if you're interested in getting high quality data using VR, have a look at our code on our project website. Okay, so I've talked about how we can get high quality human data, just use a mixed reality headset and get going. Now I want to quickly go over the second part, which is how do we create deep models for these type of robotics problems. So one of the interesting things about large models in vision and in language is that these large models are trained on uncurated data, right? By uncurated, it means that this is just experience lying on the internet. So the first question to ask ourselves is, what would happen if I trained robots on uncurated data, right? So let me just show you a small example over here. So let's say I have a data set where a robot is trying to avoid an obstacle. And of course, there'll be two modes over here where one it goes above the obstacle and the other one, it goes underneath the obstacle, right? Now, if I train a simple mean squared error supervised learning model over here, what you'll see is that the learned model would just go straight. And then at the point it reaches the obstacle, it'll just stop there, because that's what mean squared error tries to optimize, right? And so the clear problem over here is that we somehow want to learn this multimodal strategies from uncurated data, right? And so we do not want to give any signal of a reward, any signal of external human labels, right? So how do we do this? So in short, what we do is we have created a new transformer model, which is called the behavior transformer. We may not have time to go into all the details over here, but at a high level, what's happening here is that we take the multimodal output, so the ability of a transformer to give a multimodal output along with a continuous action, which we need for a robotics problem. So at the end of the day, you input a bunch of observational information into the transformer model, and it outputs a multimodal probability across the action space, across the continuous action space. So to see it in action, we have to first train this model. So to train the model, how do we get uncurated data? Well, we asked an undergrad in the lab to just use our HTC Vive setup and just play with the robot and just do anything they want to do on this robot in this kitchen environment. So as you can see here, they're just doing, you can sort of view this data as one long 4.5 hour sequence where they're just playing with this kitchen and just moving things around in a random way. So after we train a behavior transformer on this model, we can now ask the model to do things inside this environment. So let's say I want this model to open the oven door. What I can do is I can just show this model an image of the open door, which you're seeing on the top. And then in the bottom, you'll see a rollout of this behavior transformer. So it's able to do this without any additional RL fine tuning or any additional training at all. So here's an example of the moving pot example. So on the top image, we have basically moved the pot from the left side onto the right side, and we just ask the model to try to reach this target position. And you see again, it just rolls out the policy which can output this. This is the case where we are showing it to open the microwave and also open the oven. And again, you'll see our policy rollout, which should be able to figure out how to do this. So in all the examples I showed you, this is a fully vision policy. There's no state estimation being run on the scene, and it just works as a closed loop policy using the behavior transformer learned model. Again, all of our code, models, and data are open sourced. So if you're interested, have a look at our project website. So with that, I think I'm out of time, and I will end here.
Thank you. All right. Great. Yes. Oh, sorry. Audio issues again. All right. Great. So, just in the interest of moving on, feel free to ask your questions. I've been informed that no one can ask questions on Feedloop, so ask them in the chat on Zoom instead, which you can access through the Feedloop thing. So we're working on getting that fixed. But then finally, we have our third speaker, Chad. I see you there. So Chad is from Columbia University, and he is one of our Blue Sky submissions. So you should feel free to take a look at our website for his papers as well. And he's going to tell us all about his work before we move to the panel discussion. Take us away.
You can start, Chad.
Hi.
Great. Feel free to start. We can see your slides.
Okay. And a minute ago, there was a big echo. I don't know if there's still an echo.
I think that's fixed.
Okay, good. So thank you, first of all, for having me, allowing me to speak here. I wish I could be there in person, but it's nice to be here. I'm going to be speaking very differently, I think, not showing exciting results, but very much in a blue sky vein of suggesting that robots should be doing something that I think to a large extent they're not doing at the moment, which is developing episodic memories. So the psychologist William Roberts, who studies animal perceptions of time, wrote that animals are cognitively stuck in time. That is, they have no sense of time and thus have no episodic memory or ability to anticipate long-range future events. So whether animals are truly stuck in time and have no episodic memories is an open question and is disputed. And I'm not going to settle that now. But my suggestion is that robots may be stuck in time, and that although some robot agents obviously have some kinds of memories, including some semantic memories that Professor Chang mentioned earlier, and being able to replay episodes and things like that, I suggest that robots currently don't have true episodic memory the way that humans have. And so I think it would be worth investigating developing that capability, in large part because of the importance that episodic memory plays in human lives. So humans are definitely not stuck in time. Endel Tulving, the psychologist who made the distinction between episodic and semantic memory, highlighted what he called humans' ability for so-called mental time travel, projecting ourselves into the past or the future. And episodic memory and thinking about the future, including planning, seem to be linked in humans. These abilities are believed to recruit similar parts of the brain. So on the left is an fMRI of somebody remembering a sequence of past actions. And on the right is somebody imagining a future sequence. And there are other less hand-wavy examples of this and additional evidence for this linkage, including a consistent line of evidence showing that when a person has a deficit in either memory or planning, they tend to also have the other deficit. So if somebody has some kind of damage to the brain that makes them not be able to form episodic memories, they also very often are not able to plan and reason about the future, or even really think coherently about the future. It's also interesting that although people who cannot form episodic memories are able to learn some new skills, such as learning how to draw, they do so very slowly and not very well, typically. So this suggests that episodic memory formation is important for learning other sorts of skills that we might be interested in. Some psychologists who study how humans make plans believe they have shown experimentally that when people are faced with a new situation in which they must make a new plan, that they use pieces of prior episodes that they have engaged in, and they basically take parts of prior episodes and recombine them in a new way in order to respond to a new situation. So my proposal is that robots should be able to represent, remember, and recall their past actions for three main reasons. First, if we accept this idea that in humans there is a link between thinking about the past and thinking about the future, then the forces that shape how we represent past actions are going to affect how we represent future actions. And so we can't ignore half of that formation pressure and expect to get representations that are similar to those in humans. Memories of past episodes are in many ways abstractions. They leave out a lot of details, and they learn to focus on important aspects of actions. And I think some of those design choices, which basically evolution made, might carry over into helping to shape useful representations for planning. Second, just as I mentioned, is thought to occur in humans, storing episodic memories could potentially serve as a useful bank of building blocks for generating action plans in novel situations for robots. Third, if we shape representations of action sequences by planning the future and remembering the past, then we'll have a lot more training data and potentially richer error signals to shape the representations. And the hope would be that the representations would therefore be more useful and more generalizable. We would also be able to use these episodes of actions repeatedly to train memories. And so it would be an efficient way of getting more of this kind of training signal to get these representations of action sequences. So what do we need to do this? Well, as we just heard, we need lots of data. We need lots of long episodes of robots taking actions, and ideally capturing as much data as possible that the robot is exposed to in its environment. As many signals as we can capture. We shouldn't decide a priori that some things are not worth remembering, because it's precisely the learning what to discard and what to compress to remember and how to compress it that is the goal here. And second, we'll need diverse tasks. And so we have a lot of long horizon planning tasks. We're going to be hearing about them later in this workshop. And so I'll just talk about a few ways that we might be able to shape episodic memory. So my favorite maybe is using language to shape memory, because humans talk about our past actions a lot. Some people suggest language evolved in order for us to do so, to talk about our past. Some psychologists believe that our language faculty is essential for allowing us to form episodic memories. And they claim that pre-linguistic children don't have true episodic memories because they don't have the linguistic structure to structure those memories. Now, that's a big claim, and I don't know if that's true, but I think we could probably agree that talking about our past actions certainly shapes what we remember and how we remember it. So one thing that I have worked on and continue to work on is using language to summarize or narrate in detail a robot's past actions or answer questions about its past actions. So both of these tasks require certain kinds of representations of past actions and certain kinds of memory in order to work. Visual memory is also something that I think we should pursue, learning to recall and display visual memories of what was seen. And also physical reenactment. So if a robot is operating in real world or in simulation, we could ask the robot to repeat a particular action sequence, either verbatim in exact detail if possible, or in some sort of abstract way, kind of only hitting the high points and doing the important actions. And I think it will generally be important to come up with additional ways of training episodic memories, because I think we as humans use our episodic memories in a lot of ways and in a lot of contexts that we may not be aware of, and that could be potentially useful. So how do we get all this data, and do we face a kind of chicken and the egg problem? Because I'm saying we need lots of episodes of robotic long horizon actions, and we're at this workshop trying to figure out how to get that. So how do we get them? Well, first, it might be a little bit clunky, but I think we could chain together shorter episodes into much longer sequences and try to form memory representations of that. It wouldn't test the planning part, and so it would be a little bit not optimal, but it would be a way to get started. Second, we can begin in smaller sequences, both planning and remembering, and then slowly build up over time, hopefully. And then third, we might be able to transfer from non-robotics data, potentially from egocentric video, learning how to form memories of egocentric video, or perhaps less likely, useful, be text-based narratives of action, which at least have the advantage of being able to be very long if they're not very rich in different modalities. So thank you for giving me the opportunity to discuss this idea with you. And I think it's probably a long road to developing episodic memories that are as rich and useful and able to be reasoned with as we have in humans. But I think it's worth getting started trying to do that. So thank you.
All right, thanks very much. Yes, let's thanks Chad for an insightful and interesting talk. So at this point, we're moving on to our panel discussion. So I'm trying to see, we're trying to get the gallery view to pin a few of the speakers. But for now, all right. So great. I think they're currently at the top anyway because they were speaking. So feel free to answer your questions in Zoom. I'm moderating the Zoom chat. So there are a number of questions, but I think I'd like to kick it off with one. Actually, I'll start with Laurel asked a question of Angel that I think was particularly good. So Angel, you do a lot of work in these simulated environments and that many of us in the room or over Zoom, I'm sure, use. But I think, there's this question from Laurel that says, what elements or components are going to be needed to scale these sorts of approaches for more real world robots? Do you think that the vision should be that we translate simulation experience directly to the real world, or is there going to be some other component that's going to be necessary?
Yeah, so I think this is a great question. So I think we should try to have as much training as we can do in simulation. And so this means that, being able to model more phenomena in simulation, because simulation in some ways is much cheaper than the real world, right? In the real world, like how you can, but at the same time, the simulation, there's certain things that are not possible or very challenging. Like for instance, how do you deal with broken things? And so what we should do is we should encourage and a subset of the community, maybe this is more the graphics community, to be building better and better simulators. And I think this should be partly, there should be a dialogue between roboticists to not just use whatever they are given, but convince other people to build better things for them. And then I think, of course, in order to actually translate to real robots, the real robots is also has certain capabilities. And I think we need to work on defining certain abstractions that are maybe useful for people to work on, in the sense that there's ideally what you want to do is train partly in simulation, but then leverage what you've learned, and actually maybe you need to fine tune your model with a real robot or whatever. And this is not just necessarily simulation, but also goes back to some of the points Chad was making about whether can you just get leverage experiences from egocentric videos and such. But for all of that, I think what we want to do is we want to have some abstraction. Maybe this is just representations that then carry over, in the sense that what should, I think the vision people did a good job in the sense that they say, okay, object detection, that's a good problem. But what are some problems that roboticists wants to solve? What are the components? Should I be doing trying to find what part of the object can open? Should I be doing something else? Yeah.
Thanks. And then I think I have a question for all of you, but I'm going to give, then I'm going to ask Laurel to maybe answer first, because I think, it's really related to this. Is what role do you think that this sort of prior knowledge and prior data comes from? Laurel, I think one thing that I noticed is that work that you showed this from play to policy was really interesting, but it's not clear to me where prior information can be fit into such a system. So maybe for all of you, but starting with Laurel, is, what do you think we need to know in advance? How much should we tell the robot in advance, and how should that knowledge be incorporated into the system?
Yeah, I think it's a great question, right? So I think I guess there's a sort of overarching sort of question about what do we want a robot to do, right? So in a lot of these problems, we ideally want to train a robot in some small set of training environments, and then hopefully it generalizes and works in a broader set of environments, right? And I think here is where the question of what is the sort of prior or data we need in order to allow this generalization into new environments. So in the case of the play to policy work, over there, we trained it only on a single kitchen, right? So I think it's not our learned models are probably only going to work in that same kitchen, because we do not use any other priors. We do not use any object detection prior, any language prior, anything of that sort, right? So now if we have to translate from that one kitchen into or to a new kitchen, either we need to get more data in multiple different kitchens, or we need to add some priors that instead of treating it as a black box neural network model, maybe we can use things like open vocabulary object detections, for instance, right, and feed that into the model. So I think there are ways to incorporate priors into these models. The question is, what is your end goal, right? How much data are you allowed to get? How much priors are you allowed to put in the model, right? So hopefully that gives some sort of a bound on where to explore in this regime.
Great, thanks. And then I think I maybe have sort of an inverse question for Chad. So I think, you're saying that a lot of this episodic memory comes about from these existing language data sets and such. And I think one of the main ways that you said you were going to collect it was to try and give the robot these examples. In your sort of vision for how these robots should, interact with the world, can the robots continually learn, or should they continually learn, and where would that data come from?
Yeah, so I think, ideally in the kind of situation I would envision would be the robots continuing to collect episodic memories as they operate. And so through the whole course of their operation, they're getting more data, they're having more of these episodic memories, and at least that will be like a continuing source of learning for them. So how to do that, how to make sure that they're actually learning from these episodes is an open question. But if they perform an episode and then somebody gives them some feedback, maybe there's a way of pairing that sort of feedback with the episode memory, so that if they're called to do something like it again, they can see both the feedback they got and the episode track record representation. I think another way that using the episodic memories and that sort of like lifelong learning scenario could work would be if they have representations of what they did that were accurate and maybe modular, or at least decomposable in an intelligible way for them to reason over, that a user could say something like, okay, I liked the way you cleaned the house yesterday, but don't rearrange the plants or something like that, right? And so then they could go back and see, what did I do yesterday? And they could take out the parts that are asked to take out. So it would be a way for them to respond, on the fly to feedback, and then respond slightly differently in the future based on reasoning over those representations, hopefully.
Great, that sounds good. So I'd like to switch gears maybe a little bit and ask a question from Jana, talking about the idea of explicit versus implicit representation. And I think all of you have slightly different perspectives on these. So for many perceptual systems, the geometric and semantic representation is typically explicitly defined, either by a human designer or learned from data, versus implicit, as are some model-free reinforcement learned planners. And in the case of some of your discussion, the way that a lot of these natural language models tend to work. So what do you think is the role of explicit geometric or otherwise semantic representations of the world that have so far been the focus of development in the perception community? I can call on somebody. Yeah, okay. Rachel.
I guess I can start. So I kind of feel explicit representations, they are very useful for communicating, for communicating between people, maybe between people and the robot, and also for the robot to show us, some meaningful, I guess people use the term interpretability, or something that we can then interpret and understand. And I think it's also very useful to drive the training of more implicit representations. So what I imagine is that the robot will have a lot of implicit representation in the middle, but all of them, the implicit representations should be such that they can use it to predict explicit representation. so that both because otherwise who knows what on earth it's doing, but also so that we can specify what we wanted to do. So for instance, for mapping, maybe it has some neural map or whatever, but in the end, it would be nice if we can have this explicit representation of a map that says, okay, I think these things are like, I think these spaces are occupied, these spaces are not. And then I can also be able to indicate, hey, I want you to go to this position or something in a way that makes sense to me.
So I think this is actually a very interesting question, because I think in many cases now, the sort of line between implicit and explicit is also being blurred a bit. So for example, in our work, we do a lot of self-supervised learning. So we just take the vision data and automatically try to learn encoders, which is sort of trying to learn a representation from this data, right? And if you look at what the learned representations are, there is no explicit sense in, okay, it's capturing the state of object 1, the state of object 2, anything of that sort. But it is in a way sort of trying to fit in all the information about the scene inside the representation. So I guess the question is, so answering the question of should we use explicit or should we use implicit, I think now we are seeing that this line is being blurred. And so maybe options where if you can get both worlds in a way where you can get both a sense of explicitly what does the representation mean, but also the flexibility of implicit where it can learn from data. So I think hopefully that can help us figure out whether we should choose explicit or implicit.
Yeah, so thanks. Those are all really interesting. And it got me thinking a little bit on the utility of these sort of pre-trained models, right? I think, Angel, your point about, this is really good for a community building exercise, and if for nothing else, right, is that, we're training these things so that everybody can agree on certain problems that we care about and make progress towards them. But, as this is more of a speculative workshop, thinking about the bigger problems, in the long term, do we think, the panel think that these transplanted models that are trained on auxiliary tasks will continue to be a driver of progress? Or will more robotics or task-specific solutions be necessary to actually accomplish this goal of long horizon planning? I can repeat the question if people are curious. So
maybe I can give some of my thoughts over here. So I think it depends on how you're pre-training the models, right? If you're trying to pre-train a robot model on sort of pure like ImageNet data sets, it's not going to translate because ImageNet data, they don't have robots in it, right? And so in vision, when we see a transfer from like pre-trained models, it's always to other vision tasks which have data which is very similar to the data of the pre-training models, right? So I think pre-training is important, but the question is, what is the data used in pre-training? So at least from our experience at this point, we have seen that instead of pre-training the models, it's often a lot easier to just get some extra data from your environment on your robot and just give it that extra data, right? The value of in-domain data seems to be a lot more than large amounts of out-of-domain data, at least in our experiments so far.
Maybe I'll also talk a bit about, I think there are different parts, it's just different. I guess I talked about this idea of having this modular approach where you have some task planning and then you have these low-level skills. And I do feel the low-level skills, the robots, you need to have, I call them pre-trained models, but they're not the language-based pre-trained models or the vision-based pre-trained model. They are something that the robot have to, to maybe train by itself by either, kind of like what Lero is doing, where it's maybe from human demonstration or somehow but it's about, how does it control itself? How does it control its arms, its fingers, its wheels? And that's something I don't think it can get from other forms of data, language or vision. What language and vision pre-trained models, what they can give the robot is more knowledge about other world, like perception, like that's where the vision comes in. And it's like basically, and especially for things where it's more open-ended, like especially if we want to be able to pick up like a yellow giraffe, toy giraffe, and it has never seen that. So that's where those pre-trained models can help. And then there's, I guess, the idea of whether for gluing the two, and the language has a lot of knowledge about what people do for sequences of actions, right? Long-term actions, like what do I need to do to if I need to pack my bags for a trip, what do I need to do? It'll probably tell us. But at the same time, there are more specific domains, specific things, which maybe it's just better to tell the robot versus do all this pre-training.
And then, Chad, can I also ask you for a follow-up? How can your notion of episodic memory be kind of integrated into the sort of frameworks that Angel and Laurel have been talking about?
Well, first, I was thinking in the question that you asked them, I guess my attitude is that things like the language models and vision models that continually get improved and will continue to improve, that it would be a shame if in the robotics world we couldn't just sort of like quickly adapt each new advance as it happens. And so that lends itself to, I think, like a modular approach where we can hopefully plug things in. But I do think that sort of the central reasoning and how we bring these different modalities together, I think, is much more complicated in a action-taking environment where everything is real time, everything has to happen in the world, and everything has a real world effects that then have to be monitored. So I think the kind of reasoning and planning that comes together after we have these inputs from different modalities does have to be, I think, maybe much more sophisticated than we currently have. And I think how to do that, how to combine these is not clear. I certainly don't know how to do it, but I think getting, like, acting as well as bringing these together somehow in a way that's useful for robotics, but also in a way that's useful for remembering, is one way of sort of giving a little bit more training signal to this idea of combining these different modules with different modal abilities and bringing them together in a useful way. And so that's kind of why I hope that being able to form episodic memories that combine all of these things in a useful way will be one way of kind of being the center of bringing of these other modules.
Okay, great. Thanks a lot. And then we've got time for maybe one more question and some responses from everybody. But the one sort of central thing that I'm hearing from pretty much all of you is that we need a ton more data. And that, I struggle with that a little bit because we're doing the best we can with the data that we have, seemingly. And if we were to try and, generalize well, as is pertaining to the question that was asked in the chat, specifically for Lara, but also if we're going to be tackling tasks that are maybe 10 times as large or as challenging as any that we have considered thus far, where do you think that data is going to come from, and what form do you think it's going to need to take?
I think this is a great question. I think as robot learning people, we often try to focus a lot on the learning architectures and on our training algorithms and things of that sort, but we often ignore where the data comes from. So I think this is actually an important area of research as well, that how do we actually get the scale of data on robots, right? So we have a recipe that works well in vision and language, but a key component of that recipe is the data. So I think having more research into this into this field as well is, I think, what we have to do as a field moving forward.
Yeah, and maybe I'll say a few words following up. I think we can, actually leverage some of the advances in generative models to. So I'm all in simulation. I like simulation land, but this generative models, like it can generate, great language. It can generate 2D images. It can also start. There's a lot of work recently in 3D development where it's generating, you can use it to generate 3D objects. And so what I believe in is that we should be able to leverage some of all this work to basically generate synthetic environments or data randomized environment, whatever it is that will help us have new data that these robots can train in simulation, and then hopefully then it can be applied to the real world. And in particular, one thing that I'm very interested in, okay, maybe two things, is generation of scenes. Maybe Ruth will talk about this later, but using basically we can take existing models and generate scenes. And the other one is basically being able to generate objects, or maybe somehow create objects that are interactable. And that I think is still a great challenge, but I think that's a great area.
Right, great. And with that, I see Laurel has to go. So I think we're right at the end of time. Chad, do you want to maybe say something really quick, or do we want to wrap up?
I didn't have anything really intelligent to add other than I echo Angel's simulation enthusiasm, although it does feel a bit dangerous unless the simulation is really true to the real world, that the sim to real problem may end up haunting us if we rely too much on that.
All right, great. Well, it's a shame Laurel had to go, but anyway, let's thank the remaining speakers, and let's thank the remaining speakers. All right, thank you. We're going to take a 10-minute break before we begin the next panel, so feel free to walk around. I think we're going to be hanging up some of the posters. They're already, I think some of them are out there, and then I'll see you again in 9.5 minutes.
Set of panel speakers now with the focus on abstraction for this panel. So we're going to be hearing from first George Kondaris from Brown University. Take it away, George.
Thank you, Rohan. Hi, everyone. It's a great pleasure to be here. I guess I'm speaking with a hand mic, which is not usual for me. I feel a bit like Celine Dion, but I hope it comes off okay. All right. So what I want to talk to you about today is how learning abstractions is actually the whole thing. It's actually the key thing that we need to be able to do in order to produce generally intelligent robots, which is what we're all after, right? Rather than producing useful robots, which is a distraction. So I'm interested in understanding how you can build a robot that's as smart as a human, is able to do all the things that a human is able to do. And one of the things is long-term planning, but there's actually a lot of things that a human can do. But if you're trying to build a single agent, and this is the goal of AI, right? You're trying to build a single agent that can do all the things, then you face a particularly hard dilemma. If you're trying to build narrow agents that can just do one thing, then it's totally reasonable for you to assume that the agents come with a representation built in that allows them to solve that problem, that's kind of pre-built for that problem. So in the rest of AI, if you want to play Go, it's totally reasonable for you to say, I'm going to show up with a 19 by 19 array, which has like a black piece, a white piece, or nothing at every square, and that's the appropriate representation for playing Go. And if I want to, determine whether or not there's an illness in an image, in a X-ray, it's totally reasonable to say that my image is going to come in, maybe pre-registered, maybe centered on the rib cage, and you're going to tell me whether there's an illness or not. Or if I'm going to do language, it's totally reasonable to say that my input is a sentence of a particular type, and my output's going to be a question. Okay, and so the rest of AI gets to assume that their problems are pre-framed. Okay, but this is a huge mistake. This is why the rest of AI can never solve the big problem, because as soon as you start out that way, you're stuck in that box. And what instead we have in the embodied general case is that a robot starts out with an extremely rich, wildly overkill sensory motor space, which is powerful enough to contain all the other problems that it may wish to solve, right? Like definitionally, it's overkill, because it has to be able to take in, to be able to play Go and look at X-rays and also do language, right? It's got to be able to do the union of all those things. And therefore, for any one of them, definitionally, it's overpowered. Okay. And so the way to think about this model is that the robot is interacting with the world, not a problem, but the world. And it has to do that with the same sensory motor space each time. Okay. And then we're going to model a robot being given a task as being given a reward function, drawn from some distribution of reward functions that expresses what you want to do in that task. And then you can, from this, you can write down a fairly standard decision theoretic thing called a decision process, which is like a Markov decision process, but it's not Markov necessarily. And you can say, well, I can just solve this. I could like end to end just solve this for every reward function that I'm given, and I would get a generally intelligent agent. And that's true, but it's sort of uninteresting. It's uninteresting in the same sense that if you were to do one nearest neighbor, you would be able to solve all the problems, right? In the limit of data, that's true. Okay, but the limit of data is not all that interesting. So just to make it clear what the difference between a robot interfacing with the world, which is what we need for general intelligence, and a computer interfacing with a problem, which is what we get normally in AI. Let's consider the example of chess, which is about as far removed from sensory motor interaction with the world as you can get, right? It's the most abstract problem that I could think of that involves long horizon planning. Okay, so if you're a robot playing chess, this is the input and output space you have to get. You have to make decisions. You're doomed to make decisions using your motors. And you're also doomed to take in inputs using a very rich video image of the world. Okay, so like videos, not just images, videos with all the extra weirdness that comes from vision. And that has to be the case because if you assume that the world just arrived in terms of descriptions of chessboards, you couldn't do anything else. The general agent has to receive a problem in this complex a way. And what you'd really like to do is you'd really like to be able to instead do what the rest of AI does and solve that problem using a chess-specific representation. And such a representation would just, shrink this down to reflect the complexity of chess, not the complexity of your robot. A robot has to be complex, otherwise it can't be a general AI agent. But the representation you really want to play chess in is just about chess. It's not as complex as anything more than that. Okay, but building this abstraction is hard. It's really hard because if you look at all these images, which are visually very different, they have to map to the same abstraction, right? They're all the same chess position, but they're visually very, very distinct. Okay, so it's actually not a trivial problem to be able to do this. But we can write down what that means. We can kind of write down a well-formulated, precise description of what it means to build a problem-specific abstraction to frame the task in a way that reflects the complexity of the task and not the robot. So what we can do is we could say, okay, let's have an observation space that's the robot's sensors, an action space that's the robot's actions, a reward function that describes, the task in some way. And then there's a transition function. That's just how the world works. So this bottom thing over here, this is just a decision process formulation. It should be familiar to most of you. And what I'd like to be able to do is I'd like to be able to build a maximally abstract decision process formulation at the top that reflects the complexity of chess. And one way to think about that is that it allows you to choose high-level actions and only use high-level inputs, but still achieve a high return based on your task description. Okay. And it turns out that we understand now very well that you only need to do two things to build this. So one of them is you need to build perceptual abstraction. So you need to take in your complex sensory motor input and possibly its history and build an abstraction over that. And the other one is that you need an action abstraction, which is that you need to be able to take your high-level actions, build high-level, your low-level actions, build high-level motor skills out of them that are task relevant. And if you can do those two things and they're well matched with each other, then you can produce an abstract decision process. And if that abstract decision process is maximally compact, but still achieves high return on your reward function, then you've kind of got what you want. Then you've got a problem-specific representation. Okay. And just to sort of make the argument that this is a maximally general thing. So imagine you've got this decision process formulation, and imagine that the robot builds an abstract decision process, and now it can look at its properties, right? Because it built that decision process, it has it inside. If you take that decision process and it happens to be observable and it happens to be sequential, then you've got an MDP. And if it happens to be deterministic, known, and discrete, then you've got search, and you can swap in A star. And if it happens to be factored, then you've got strips. Okay, so these things are all just special cases of the deterministic of a decision process that have to do with the structure of the problem, not the structure of the robot. Okay, so the robot's going to build a problem-specific structure, decision process, and then exploit the properties of that decision process to swap in an efficient algorithm like that developed by the rest of AI, right? There's no reason to do anything except alpha beta pruning for most games because you can get to average human level player out of the box with zero sample complexity once you're in the right representation. And for example, if the problem's adversarial, you can get adversarial search, and you can do this for like all the classical AI decision-making paradigms. So if you start out with a decision process that's observable and it's not sequential, it means it ends after one high-level action selection, and the actions are discrete, then you have a contextual bandit. And if you have demonstration data for the contextual bandit, then you have supervised learning. And if the actions are not discrete, they're continuous, and you have demonstrations, then you have regression. Okay. So we can get to all these classical, all these existing classical AI things, as long as we can build these problem-specific representations that we can index into the picture. Okay, so the sort of general view that I'd like to promote here is that we can imagine a robot with a wildly overkill sensory motor space because it has to have, because it's general. It's going to go around and solve problems by building the appropriate task-specific representation and then swapping in a problem that matches, an algorithm that matches the structural properties of that problem-specific representation. If it's learned a decision process for playing chess, it's going to swap in minimax and alpha beta pruning. If it's learned one for just navigating around the world, it's going to realize that that's a discrete graph and it's going to swap in search. And if it's doing robo soccer, then it's going to learn an abstract perception and action space that are continuous and look like vectors. And maybe it's hard to build a model for that, so it has no recourse but to do policy search. Okay. Just to show that this isn't a totally crazy thing to do, I'm very quickly going to show you a video that we spent a long time getting. And in this video, we assume that you're given the high-level actions. Okay, so you build the high-level motor skills. We're going to show that you can learn a symbolic representation that matches them using very little sample data. So here is a room. This is a picture of a room. You can see the robot in the room over there. There's a cupboard. That's the cupboard. There's a switch. That's the switch. There's a cooler. And I just hand wrote motor skills that move the robot between the cupboard and the cooler, that turn the switch on or off, that open or close the cooler or the cupboard, and that pick up something if it can see them inside the cooler or the cupboard. Now, there's a couple of natural restrictions here. If you open this cupboard, it blocks access to the switch. Also, if the switch is on, there's a light inside the cupboard, which is so bright that it whites out the robot sensors inside the cupboard. You can't manipulate anything in the cupboard. And finally, you need both hands. This is a dual arm robot to open the cooler and open the cupboard. Okay, so you and I could immediately write down a factored MDP description of this problem. It would be tiny, okay? But the point is we would like the robot to learn it from sensory motor data that looks like that. More specifically, we're going to input the robot's position and pose in a map, a voxelized grid of the entire room. I'm just showing the cooler here, but it's the entire room in one go, and the robot's raw joint positions. And if we just run those sensory motor actions, and here we're going to run about 160 sensory motor action executions, not of each skill, but just in total. It takes about an hour and a half. You can see the robot opening and closing the cooler, picking up the object, moving it around, turning the switch. You can see, and there you can see the switch is blocked by the cupboard. You can see when the switch is on, it's very bright in there. It whites out the AR tag, which tells the robot where to grasp the object. From that, we can automatically build, just using machine learning and a bunch of math that my students and I have done, a symbolic representation of state that is provably necessary and sufficient for planning with that set of actions, okay? So it's a text file. It's unarguably symbolic because it is just that text file over there. This says if you want to navigate to the cooler, precondition is that your robot state is drawn from a distribution called symbol 1. So if we visualize symbol 1, we see that it refers only to the robot's position in the map. And if we draw some samples from that and we put it on the map, you'll see that the robot is distributed in a way that it's facing the cupboard. And afterwards, that won't be true anymore. It'll be drawn from symbol 0. That means that the robot is facing the cooler. So if you want to navigate to the cooler, you better be standing in front of the cupboard. Afterwards, you won't be standing in front of the cupboard. You'll be standing in front of the cooler, and that will take 37 seconds on average. Here's a more interesting operator. This says if you want to open the cupboard, you have to be standing in front of it. Additionally, symbol 3 has to be true. That's a distribution of the robot's joints. You notice when it picked something up, it held it up here. So this means it's not holding anything. Okay, the hands are down there. And then symbol 4 is a distribution over the voxel grid, and I've just cut out where the cupboard is. You can see that these are samples drawn from the cupboard. Afterwards, this distribution will change to this distribution. The cupboard used to be closed, and now it's open. Okay, so this is learning from raw sensory motor data plus a little bit of compression. You can see compression artifacts happening here. It's happening from on average 10 motor executions per skill. Okay, so on a real robot in real time. And then afterwards, you can ask it to plan. So I'm going to ask it to move this object from the cooler to the cupboard. It takes 4 milliseconds once you have that text, once you have that representation, because of course it's tiny and classical planners are really good at this. So we just drop in a classical planner. You'll see it open the cooler, and then it'll see the object, but it won't pick up the object because if it does, it can't open the cupboard. So before it picks up the object, it will move to open the cupboard. And then it won't open the cupboard because if it did, it wouldn't be able to turn the switch, which has to be off. So first it will turn the switch, then it will open the cupboard. Then it will go back and get the object. Okay, so that's classical planning doing what classical planning classically does, which is unsurprising. What's interesting about this is it would be very hard to do that in pixel and torque land. So what's happened here is because we've successfully gotten the robots to autonomously learn a tiny compact representation with which like long horizon planning is really, really easy because that representation, those algorithms were built to exploit the structure in problems like that. Okay, so it's going to put the object in the cupboard and then I asked it to clean up. So it's going to close the cupboard and close the cooler. Okay. I have 3 more minutes. Is that right, Greg? 3 or 4 more minutes. Okay. So we've been working on this for a long time. We have now deployed it in 12 different cases. Some of them are directly, this is kind of dark, but this is learning object-centric representations for Minecraft. Well, let's see, 1, 2, 3, 4, 5 of them are on real robots out there in the world. So it's now a well-developed framework. 2 kind of immediate consequences of this framework that I'd like to point out of this way of thinking about abstractions. One of them is that there should be a lot of reuse. If you take the sort of machine learning view to say that we're going to learn these things completely from scratch, and you learned an abstraction hierarchy for chess, and then another one for moving around in the world, and another one for playing soccer, you would find that there's a lot of repeated learning going on. Okay. Of course, there's a lot of repeated learning going on because there's structure in the world and in the robot that we should be exploiting in order to be able to speed this process up. So you could imagine putting a line here and saying everything below that is exploiting structure in the world or the robot and should be built in, should not be learned from scratch. So we call this the sensory motor substrate. Okay, and the way to think about this is that this is what robotics has been doing all this time. Okay, so if you look at everything that happens in robotics and computer vision, you can think about it as either abstraction over observation hierarchies. For example, SLAM takes a partially observable navigation problem, localizes in it, that turns it into a fully observable navigation problem and builds a map, which is a model for that fully observable thing, so you can do planning in it. Okay, computer vision takes a raw bunch of pixels and then says, okay, here's the 7 objects in it, and maybe here's a description of their features. That's a perceptual abstraction. And like motion planning and deciding where to grasp and planning through a map, those are action abstractions. Okay, so we could imagine organizing robotics, taking all these things that have always been done somewhat in isolation and matching them together, saying actually that they consist of very tightly matched perceptual and action abstractions, and that these perceptual and action abstractions exploit the first few layers of what is common about what is common in the world, and would allow us to drastically bootstrap this kind of learning. Right? If we couldn't do object recognition, it'd be very hard to do something like teach someone how to play chess or how to build a representation of chess in, you know, like an hour, which is how long it takes a person. One other implication is language. So, and Brown is really good at this. I'm not the most important person at Brown. I'm not even like the 3rd most important person at Brown doing language. But just to point out that this suggests that we should think very hard about grounding language in decision process formalisms. Okay, so you could imagine that you've built this whole hierarchy and then someone says some language, and it should be grounding to these various different levels of decision processes. And that if you want to think about how you ground language, it's a communication protocol devised by robots solving decision processes to talk to each other. It shouldn't ground into language. It shouldn't ground into vision or video or Twitter text. It should ground into a decision-making process. Okay, and so we've done some work which we thought was quite nice to try and exploit these large language models by building a language that's specific for decision-making processes called Erlang. And if you do natural language to Erlang just as a using like GPT-3 codecs, just as a machine translation thing, you can actually get really nice results. Okay, so just before I end, almost on time, what I want to emphasize here is that, you know, we always talk about abstraction like it could be a nice thing to have, but I think that getting over this, you know, if we're trying to build generally intelligent agents, first of all, they have to be robots. Robots are the only things with rich enough sensory motor interfaces with the world to be able to solve almost anything you can give them. And one of the reasons that should be clear is because you and I are robots, not computers. Okay, there are no natural agents that are computers but not robots. Okay, the thing doesn't exist. It's not even clear that it's coherent. But if you want to build a generally intelligent agent, that agent has to have a wildly overkill input and output space because it has to be able to handle the union of all the problems it's ever going to be asked to solve. And so that creates a dilemma. The more general purpose the agent is, the harder it is for it to solve any individual task. And so I think the core question in general AI is how do you get over that dilemma? And the way that you do it is you learn a problem-specific representation that captures the complexity of the problem, not the robot, and then you use one of these algorithms that AI has developed for us over the last 50 years that have been built to exploit this kind of structure. Okay, that's me. Thank you. It's IFRA next, is that right?
Thank you, George. Thank you very much, George. That was an awesome talk. Next up, and we'll hear back from George at the panel in a bit. Next up, we're going to have Ifra, who is joining us remotely and is going to be doing a pre-recorded video due to unstable internet. So can we play the pre-recorded video?
Everyone, my name is Ifra Idris. I am a fifth-year PhD candidate at Brown University. I'm a part of Human to Robots Lab and Big AI at Brown. Today, I will be talking about designing long horizon social interaction. Now, as conversational assistive home robots are becoming a part of our daily lives, for them to be an effective assistant, they need to be able to guide the humans to accomplish various daily tasks, such as cooking meals, performing exercises, or operating machines. These long-term social interactions, they not only are going to span over minutes, one task that the human does, but it can also require the robot to monitor the environment for days, weeks, or even months. And in such a scenario, what is going to happen is that, for example, if we have a robot, this is a map of our robotics lab environment where we allowed robot Harry to monitor the environment. And at every time step, the robot got the robot's position, its limited depth information, and as it operated in this environment for long periods of time, our robot, which is like Curry shown on the left, gathered all of these observations of the objects in the environment. Now, given these observations, the robot must estimate the state of the environment, which includes the environment and the user's goal and intention. However, estimating the environment and the user's state is very challenging because it includes certain sources of uncertainty which lead to inaccurate state estimation. These include, firstly, partial observability, because the robot will only be able to gather observations of the objects that are in its field of view and also of the human if it's in its field of view. Further, the sensors and the tracking algorithm, they are noisy. Here I'm demonstrating the state-of-the-art deep learning object detector algorithm, YOLO, which is doing a really bad job at being able to detect the object that the human is interacting with, which is a book. Sometimes it thinks it's the laptop, or sometimes it isn't even able to detect that something is in the hand of the human. Now, partial observability and noisy sensors, they actually lead to an inaccurate interpretation of the world and the user space, which can adversely impact the long horizon social interaction. So my research actually deals with this very question, that is, how can we handle uncertainty for long horizon robotics? And for the rest of the talk, I have divided my research into 3 phases. The very first phase is where I will talk about my work, which deals with uncertainty in the world state estimation or the object state estimation. And when we further extend it, we know that the humans are going to be interacting with the objects in the environment for accomplishing a task. And I am going to be talking about how robots can deal with uncertainty in the user state. And further, the user might not be just doing one task, but might be interleaving or be doing multiple tasks at a time. And for that, we are going to talk about how can a robot deal with when there is uncertainty in the task specification. So for the first part of the talk, which is like uncertainty in the world state, we go back to the same motivating example. The robot operating over long periods of time is going to gather all of this massive amount of observations of the world. In such a scenario, a human might ask for assistance by asking a spatial query such as, hey Curry, or hey robot, what are my top favorite locations to place my keys and watch? Or it can ask a temporal query such as, when was the last time you saw an orange pole? Now, a robot which is trying to estimate the state of the objects in the environment, it might not in scenarios where it wouldn't know the queries in advance, and in scenarios where it wouldn't know the object detector that you might be running on each frame, for answering such a query, that robot needs to run will take a really long amount of time, because it will have to search over all of these observations, which include countless partial view detections of objects. And must I say, they will have repeated partial view detections of objects, and which will make answering such queries really time efficient. So to handle this challenge and to improve or reduce the uncertainty that might be caused because of the object position, by the robot's position, or by the object detector, we actually introduce a novel formalism which does three-tier clustering of the object observations to make a long-term spatial temporal semantic map of the surrounding environment, or of the objects in the surrounding environment. I'm not going to go into detail of this, but I'll be more than happy to talk offline. We also have some quantitative results where we show that our algorithm, which we call as D3A, it is way more accurate, 81.98% accurate as compared to the naive baseline, which does not do any association of these partial views over time. So it's not reducing any uncertainty. And our algorithm, because of our algorithm actually takes way less time, which is 24 milliseconds, to reply to a query as compared to the baseline, which takes 1,137 milliseconds. And this correlates to improved user experience. Now, moving on to the second part, which includes uncertainty in the latent state. So over here, again, if the human is trying to complete or accomplish a task, such as in this case, making a breakfast, given these observations, the robot needs to estimate the plan, that is, what's the next step that the human might do so that it can assist the human accordingly. Please note that in a maximum sensor smart home state, where we are getting perfect world state information, the robot still needs to do this recognition or an estimation of what is it that the human is going to do next. Or in the broader aspect, given these observations, it needs to estimate what is the goal that the human is trying to do. Now, previous works exist which have tried to do goal and plan recognition as planning. This was the term coined by Ramires and Gaffner in 2009, and a lot of work has been done since then, which use a handcrafted task specification to do goal and plan recognition as a human completes the task. But these works, they actually make a lot of assumptions as to whether the human is always doing an optimal action, whether they're interleaving between the tasks. And to actually handle these challenges and handle these sources of uncertainty, what that is uncertainty in latent variables, what we introduce is this novel algorithm, which actually represents the human as a hierarchical task network. That is, the human as a high-level goal, which can be subdivided into these sub-goals. And we also make an assumption that the robot is actually a PALM-DB planner, which, given the observations, does belief update and goal recognition. And in scenarios where the robot is actually uncertain as to what is it that the human is trying to do, it asks clarification question and uses the language feedback from the human to update its belief. We call our work Dagger PalmDB, which is Dialogue Goal Recognition PalmDB. And we find that our Dagger PalmDB planner, it asks 66% fewer questions than an always ask baseline, which always asks the correct question. And it is still, by asking way less number of questions, it's able to achieve 86% high accuracy, which is just 1% less than a planner which always asks the right question, and this is 8% higher than a baseline, which assumes that the human is an HDN, but it does not ask any questions at all, which is very promising. And further, let's move on to the third phase, where up till now, we've assumed that we have task specification predefined for us when we are trying to do plan and goal recognition for the human. We are assuming that this hierarchical task specification, it exists. However, building and or all learning generalizable task specification from scratch is very expensive, both in terms of data collection and both in terms of learning time. So what we propose is, how can we generate a hierarchical action graph structure by iteratively prompting large language models? Because we've been recently seeing that the large language models have been shown to be really expressive in terms of generating sub goals for a given task. And we aim to do it in a weekly supervised manner. However, the way we are trying to use large language models is that the sub goals that the LLM might produce, it might not be the primitive action, but might group other multiple non-primitive or primitive actions together. And the way we hope to evaluate our HCN is both in terms of structure, in terms of its soundness, and in terms of its completeness. So overall, with the 3 phases that I've talked, I have talked about how we can deal with various sources of uncertainty in designing long horizon social interactions. And overall, what I'm trying to advocate with my line of research is that in long-term social interactions, using hierarchical spatial temporal structures to model the world and the user state can enable the robot to have a more accurate and more time efficient online state inference. Thank you so much for listening to me, and I'll be more than happy to take any questions. Thank you.
Thank you so much, Ifra. And I forgot to mention that was one of our early career Blue Sky talks. So please, if you're interested in this line of work, do check out the paper linked from our website. For our last talk before the panel discussion, we're going to have Jitendra Malik from Meta and UC Berkeley.
Okay.
Take the mic.
Finally. Which one?
The one you're using. Anyone that works.
Hello, can you hear me? Okay. Can people in remote land hear me? Okay, so fine. So the philosophical remark that I wanted to make was that for any long horizon problem, I think the right way to think about it is skills and composition of skills. And I prefer this way of thinking about it rather than abstraction, because abstraction takes us back to sort of symbolic AI, whereas I sort of believe in sensory motor control loops and then composition of them to get more complex behavior. So if you will, you can think of layered architectures from Rod Brooks and so on. So this is a philosophical debate we could have forever. So I'd rather do it with concrete examples. So I'm going to give you two concrete examples, one which is about navigation and one which is about mobile manipulation. Okay. So let me get to this task. So this is a real world task. And the goal here is, and actually we did this experiment in the real world with by renting Airbnb apartments. So we rented Airbnb apartments. We walked in with a robot. It's put inside the house, and then it's told, go find a chair, or go find a plant, or go find the toilet. So in this case, this robot was instructed to go find a plant. So can you see it? The robot is in front of the TV, but there's a plant there. So the task is go find a plant, and that's it. You come with nothing else. There is no pre-mapping, no SLAM, nothing. You bring the robot in, you put it inside the house, you press a button, and you say, go to one of these targets. And you see the targets here: chair, couch, potted plant, bed, toilet, etc. Okay. What you are seeing here is, so let's note what are the components here. On the left top, you see the observation. So this is what the camera of the robot is seeing. At the bottom, it has built some kind of a map. And this map is not the same as a SLAM map. Okay, I think the SLAM does too much and too little. It does too much in the sense that completely mapping any space is not necessary. When you go to a friend's house and you have to go to the toilet, you're not going to ask for permission to run a SLAM algorithm over their entire house first. You're just going to go because you have good heuristics for finding bathrooms. And that's the way these tasks should be done. Okay, the second point is that SLAM doesn't capture the semantics. You want to know where are chairs, where are tables, where are kitchen knives likely to be found, and so on. Okay, so here's another example, and this is going to be, so these are real runs. This one, there's a different goal. The goal is find a chair. Okay, did it find a chair? Yeah, it's a chair in front of the desk. Okay. Okay. And what you see at the bottom is the semantic map, which is not the same as a SLAM map. And actually, we did this in zillions of places. We went and rented Airbnb apartments. We specified different target goals: find a chair, find a plant, find the toilet. And then we compared 3 different approaches. And I mean, I'm trying to tell you the lessons we learned from this approach. So we started with, okay, first of all, there's a classical baseline. So think of it as SLAM++. So basically, there's a geometric map as SLAM would construct. In addition, you need to have some heuristic exploration strategy, right? You're just going to, you're going to build up the map, so you need an exploration strategy. And the exploration strategy is uninformed, because the SLAM algorithm is uninformed. The SLAM algorithm has no training in it, right? You just go and explore, you do it. It's like uninformed exhaustive search. Okay. The second approach, which is like the popular thing these days, is what would be end-to-end learning. So end-to-end learning here means that we train in simulation, and there are good simulators available and good environments for homes and so forth. So you train in a simulator, you train a policy, and that policy is going to try to find a chair or try to find whatever. So there's this training with 77,000 human trajectories and 200 million frames of RN. So that's end-to-end, from pixels to action space. So that's one approach. And this would be like considered like the canonical learning approach. And then there's a third approach, which is what we will show turns out to be much more successful. And that's why I believe that it is not, the secret is not end-to-end training. End-to-end training for thousands of different tasks is not going to work. And in fact, it's an inferior solution. Okay. You need to have some skills, and then you need to compose them. I think that's the way I like to think about things. So here, modular learning, there's a semantic map, which you can roughly think of as not a complete geometric map, but this will have labels of the type a chair, a bed, table, things like that. And then the exploration is goal-oriented, and this is itself learned in simulation. So in simulation environments, you learn what is a plausible path to get to a toilet, or what's a plausible path to get to a chair, which is based on the typical regularities that you find in a home. Okay. And then, so this gives you sort of more details on this is what the end-to-end policy is. So you have various neural networks analyzing the image, and basically you have some kind of a GRU which keeps track of the past. And modular learning is actually quite intuitive. So you are going to explore the space, build a map, and the map is semantic, but you don't build a map of the whole thing. You just build a map of the areas you're going, and you're always directed by what's more plausible. If I'm going to try to find a chair, what's a more plausible direction to go? So there's this 3D semantic map, and then there's a goal-oriented semantic policy. Okay, and you can train this in these various simulation environments. And the results are, in simulation, everything works really well. Okay. And so you might say, done. And this is what happens in the real world. Modular learning works, in fact, better than in simulation. And the reason is that actually the object detectors work better in the real world. Then, because in the simulator, you have some labeling errors and so on. The classical approach does reasonably well. And what's an absolute disaster is end-to-end learning. Okay. So, and then we tested this in various ways. So there are various metrics for judging the quality of this task. But this was quite surprising and convincing, in the sense that normally we are in computer vision. I'm used to this game where one approach is 56% and one is 58.3 and so on. None of this. The gaps are huge. Okay. So modular learning is reliable. And so I'm saying that what this says to me is that there is compositionality here. So the compositionality here is there is an aspect which is about building up semantic map. So that's one behavior, one skill. And another aspect, which is what's the next most likely place to go if I'm looking for a chair or a dog or a giraffe. So these two are being combined. And if you think about it, that's a very natural thing when you're for doing this task. And the composition of these two, which have been previously trained, leads to a sort of success out of the box. I'm telling you exactly what we did. We rented an Airbnb apartment. You open the door, you put the robot in, you press a command, find a chair. Okay, find a toilet, and so on. And these are results from that. So these are very convincing experiments in terms of how this will work out in the real world. And they are arguing for the composition of two skills. One is map building, and the other one is this plausible path kind of behavior. Okay, and there are more examples, but I won't belabor the point because the paper is available on arXiv. End-to-end fails to transfer for a variety of reasons. Okay, I have this. What happens is that there are gaps of various sorts. So for example, vision gaps. So a basic thing that we need to know is RGB in simulation. There's a significant gap between RGB in simulation versus RGB in reality. Depth, not so much. But and therefore, if you have trained your detector for find a chair solely in simulation, that detector will not work as well as a detector which has been trained in the real world on tons and tons of data. So we want to compose modules which have been pre-trained and so on. Okay. If we have do we have time to talk about another aspect, which is multi-skill mobile manipulation for object rearrangement? And this is a paper which is also on arXiv, but I'll need to switch to a different video. So let me stop. We have done a stop share. Okay, great. And then okay, do you see something? Yeah. Okay. So this video explains the task of multi-skill mobile manipulation. So this is, let's play this out. So I'm going to periodically pause it to make a point. Okay, so the task is in some kind of a home, it's mobile manipulation. So it's a rearrangement task. So you have to take some objects from the table and put them somewhere else. Maybe you take the apple out from the fridge and put the dining table, etc. So there is a home assistant a benchmark for this, and there are versions of this around. And these are done in simulation in a fairly with fairly realistic models, in the sense that the model of the environment is from real scans, objects have been built out of it, etc., etc. Okay, so there are versions of this which are, so this is from sort of a Facebook team. They work like this from Stanford and so on. Okay, so now so think of that that full task is a long horizon task, right? There's some rearrangement of the room to be done, and we can imagine several such tasks. Okay, put away the groceries, set up the dining table, and so on. And what would the end-to-end philosophy say? The end-to-end philosophy would say, train for each task separately. And this is a bad idea. And we find that when we try to do that, the performance of those approaches is very poor, end-to-end training, just like we found for the navigation task. What works well is having good basic skills. So good basic skills, what do I mean by a skill? A skill is a sensory motor control loop. So an example of a skill is pick. An example of a skill is place. An example of a skill is opening a fridge door. An example of a skill is navigate from point A to point B. And if you have trained each of these skills well, and then you can compose them together to solve the long horizon task. I mean, it seems kind of intuitive, and the idea is like, goes back to strips, right? At least. Okay, the difference is strips acted as if each of those operators just had some preconditions and post conditions, and the assumption was the operator would just work. Whereas each operator, if you make each operator into a control loop, a policy, okay, I think now we are talking, and we need to do, strips was in the symbol. When you're manipulating an object, you can move while you're trying to manipulate the object. So anyway, and then I'm not going to try to pull up the slide which shows the numbers, but again, the results are very stark. You try to train end to end. Basically, if you have a sequence of 8 or 9 tasks, that policy just dies after 2 or 3 tasks. When you have this compositionality of skills, then it turns out that you get very good behavior. It degrades a little bit with every step. So if you have a 11-step problem, you're less likely to succeed than for a 3-step problem. But the degradation is like by 5% at each stage. And how to compose the skills, there's a bit of hand design here, okay? But I think the general idea is correct. Train skills, compose them. I'll end here. And I apologize to all local and remote people because of all the AV chaos. Okay.
Thank you so much. Let's all thank Jitendra, and please don't apologize. It's okay. So now we're going to have the panel. So can we have George come up? Jitendra, please. You each can grab a mic, maybe. Do you want to try that mic there? Maybe. Yeah, maybe. I don't know. But just let me see if it's on. Okay, so try it. Okay. Try speaking in. Okay, and yeah, and we're also going to have Ifra, of course, but joining us on Zoom.
All right.
Just because. Yeah, this is the one that just jotted.
So Ifra, we can see you up here now. Can you just say something? So mic check.
That sounds good.
Okay, so we can't hear Ifra, but we can see you. Okay. Should we? Okay, we'll get started. Okay, so yeah, hopefully we can sort out the audio issues for Zoom. But this is awesome. So I want to start with a very general question, which is, I think that through these talks, we've heard many different sort of interpretations of what abstraction means, from symbolic kind of abstractions as a transformation of state and action spaces in George's talk, to kind of hierarchical task networks that break down goals in Ifra's talk, to talking about composing skills for building modular navigation methods in Jitendra's talk. So my question is, like, is there any hope of viewing all of these different interpretations as like really one and the same thing seen from different angles? Is there hope for unification, or are we all doomed to be working independently on our own projects and not really ever be able to unify things in the long run? Whoever wants to start, maybe.
Okay. I hope so. I mean, to me, the proof of the pudding is in the eating. So I want to start with, let's say, go back to the 1960s and computer science, right? So programming languages. What was the power of programming languages? The power of programming languages is that we could write programs and then we could combine programs to write other programs and so forth, right? And we had a very convenient abstraction, if you will, in which we operated. So that's what we are after, right? Because we don't, to me, training a separate skill for every task is not a scalable solution. It's like writing a long machine language code for, sorting an array of 7 numbers, and then you write a separate one for sorting 11 numbers, right? So that's not scalable. So now where we disagree, potentially we disagree about, is what are the right primitives which we must compose together, right? Okay. And I have my conjecture, which is based on the fact that I think the era of training skills seems to be moving quite well, because we can train skills in 2 ways. We can train skills with reinforcement learning. We can train skills by imitation. And these are both techniques which scale nicely with sort of data and compute. And we are making a lot of progress on skills. What we are not making lots of progress on are long horizon problems which require that sort of composition. And the amount of work we have on that is little bits and pieces here and there. And I'm not claiming I have any general solution there, but we need more people working on it. And after a few years, I think a pattern will emerge. So I'm pretty humble about how it's going to be.
Ifra or George?
Okay, I guess I'll go next. So I just want to say, first thing, I come from the hierarchical oral literature, so obviously I agree with a great deal of the stuff in Jitendra's talk. We've been training skills for a long time. Preconditions need to line inside effects and all that stuff. I think that it is clear that now we're going to be needing to learn large libraries of reusable skills. I think that's been clear for a while, but now we're beginning to actually be able to build those in real life, which is wonderful. I think, the options framework has like a nice description of what a motor skill looks like. It's nice, it's closed loop, it contains all of these things. For me, that model is like the right API to think about a sort of composable skill. I think what we're missing is the sort of right API on the combined state and abstraction, state and action abstraction thing. And for me, it's a decision process, right? So it'd be really nice to be able to write a piece of software that says, okay, you show up with your reusable motor skill, and then you build some perceptual abstraction that's attached to it that can help you reason about whether you plan with it. And those things will just like incarnate in some programming language, a decision process formalism for you, and you can compose that at runtime, and it's all just kind of there and uniform, and maybe it looks like a ROS service or something like that. I did want to say that I think the distinction between the sort of symbolic and not symbolic thing is a bit of a red herring. They're all just perceptual abstractions. Some of them happen to be discrete and maybe even deterministic, but that's just, it's really about what abstraction the problem demands. Some problems demand discrete abstractions and some demand continuous abstractions, and we should be able to treat them all uniformly. And so I think the notion of a state and an action abstraction and those things matching against each other feels like a natural way to do that, to me anyway.
Ifra, hopefully we can hear you now. Let's see.
Okay, can you guys hear me?
Perfect.
Okay, cool. So yeah, thank you for having me. First of all, I'm really honored to be talking with George and Jitendra. So I'm extremely honored. For the question that you asked, I think it really I extremely agree with Jitendra and George, both of them. And whatever I'm going to say, it's going to come from the course that I've taken from George and reintegrating AI. And the very first slide that George talks about is on the necessity of abstraction. So I think that when we are trying to the question that you ask, it really depends on the problem that the agent is trying to solve. Is it trying to be like, is it trying to solve or go towards the narrow AI domain, or is it trying to go towards the general AI domain? But in both the cases, it's the various assumptions that are making, which are leading to these different formalisms. But one thing we all agree is that abstraction is definitely needed. So I agree with Jitendra that a lot of advancement is being made in skills, but what now is needed, like a proper API or formalism for composing those skills or combining the state abstractions with the action abstractions. That's what is going to lead to like further advancement. So yeah, I hope this helps.
Yeah, this was a great answer. I tend to agree that that a lot of when people talk about skills, they're often thinking about kind of actions. But at the same time, we also have to think about our observations of the environment. Yeah, I mean, Jitendra, do you want to respond?
Yeah, so no, I don't think we have any really major disagreements here. For me, a skill is not an action. A skill is the full control policy. A skill is a policy which has both perception and action. So there's a perception and, I mean, you perceive, you act, right? That whole control. So control theorists will just call it a control loop. So there's a feedback control loop. And I mean, MDP came out of the control theory literature. I mean, Bellman was a key person in both of these things back in like 1959 or whatever. He actually has a great paper which he tries to do something similar to what George was talking about, which is he wants to have in this grand way of thinking about stochastic problems, deterministic problems, what a standard control theory person would have. There would be these more discrete spaces, which is where MDPs came in. And I mean, I think we are all after the same thing in that sense. To me, it's really, we have to make big sort of empirical progress. So the empirical success of hierarchical RL is not that great, right? What practical people do is they hand design the hierarchies. I would love for it, and I've hand designed the hierarchies. I've cheated, right? Both these pieces of work, we hand designed the hierarchy. But ideally, we would like that to emerge, right? So that's, I think, the challenge now. My belief is in the deep learning era, the way we have made progress is by just tackling lots of problems head on. And then you find that some approaches are dead ends and some are not. And once we see enough successes of these, serious long horizon problems being solved, I think then we will abstract from them. There needs to be a variety, right? So if you just solve the problem in one domain, you won't necessarily learn general lessons. So we sort of have to do the process of science, try things in lots of ways, and then we'll hopefully we'll see a pattern which we can then.
Absolutely. And this brings me to like a question which I've been interested in, which is, I think everyone in this room and on Zoom wants to solve long horizon problems, but often when we look at especially RL literature, long horizon means 10 actions, which is not really long horizon at all. So one thing I've really been wondering is, what is the fundamental thing stopping us from scaling up? Is it just a data issue that nobody has the capability to make a really long horizon data set? Is it even sensible to have offline data sets for these kinds of problems? Or are the issues more on the algorithmic and computation side?
Okay, so I think there's a computational complexity problem that has to do with long horizon planning, right? Planning is typically exponential in the horizon, and there's just like, you can't get away from that. That's just like a fact about the world. The sky's blue and planning is exponentially complex in the horizon. And so I think the hierarchical sort of way around that is to say, yes, but we almost never actually solve a very, very long horizon problem. Almost always we transfer the problem into, using a hierarchy, using some level of abstraction, we transfer it into a not so long horizon planning problem. To get here, I flew across the world, but I don't think I made more than 5 or 6 decisions about which airport to fly out of and where to go. And even that was a bit of a pain, and so I think like a lot of things in real life, sometimes if you find yourself solving an extremely hard problem, you're doing it at the wrong level of abstraction, and you should be trying to pull an extra trick. At least that's my I don't think more data will solve it. I think the data stuff it's not magic, right? And so if there's exponentially many plans, you need exponentially more data, and at some point we run out of like time in the universe. So that's my feeling. I think long horizons relative to the robot plant, and so you should be transforming yourself into a problem where the horizon isn't actually that long effectively. I don't know if that makes sense.
I mean, I agree fully. I think where you want more data and more compute is in making each skill more robust. So I feel that when you're composing a bunch of stuff together, each one needs to be much more reliable, or you need to have the fallback policy for, if I'm putting an object on the table and it falls, what do I do, right? So you may need an outer level loop or whatever, but data and compute should help you make each skill better. And as a vision person, I would also argue that we need to make effective use of sort of sensory data. And we don't necessarily do that. So I think the old style robotics people would magically assume that computer vision will deliver to them the pose of an object perfectly. And okay, this is nonsense. This is asking for too much. Okay. Perception is actually much richer than that, but you have to sort of use it in a more subtle way. And of course, it's not just vision. I mean, the proprioceptive state of the joints is very informative. I mean, touch is very informative, right? I mean, I think when I compare a biological motor control problem with what our robots do, I mean, the parallel jaw gripper. I mean, in 1980s, I got my PhD in the mid 1980s. At that time, computer vision was very in a pathetic state. We used to have 3 images in which we used to show our results. And today there are probably 1 trillion photos on the web. Everybody in the world is roaming around with a gigapixel camera. Okay. My colleagues in robotics, they had a parallel jaw gripper then. And if I look at my colleagues today, they have a parallel jaw gripper today. So obviously, the sort of the sophistication, that tactile sensing and multi-fingered hands and so on. I'm not saying that it's not being worked on. Lots of work is being done on it, but it hasn't captured the mainstream the way everyone in the planet roams around with a gigapixel camera. So sensing has to be taken seriously, and it has to be taken serious. So take it seriously, but not literally. So don't assume that vision can magically deliver these things. Okay, so I think that that's part of the answer, because biology tells us that the perception part is very important. And then, I think that this is where compute and data come in training those skills. I think above that, it's not the brute force approach will fall for the reasons that George mentioned. The exponents, you can just postpone them by, 2 steps if you have more compute, but we do need an abstraction. When I came to New Zealand, I was not planning my footsteps for every millisecond as I'm walking in Auckland Airport, right? This is nuts. So therefore, I think the end-to-end paradigm has to give way, because it's the most popular paradigm today, and it needs to give way.
So Ifra, I want to turn the question to you, and maybe I want to make it a little bit more specific also, because one of the things I was thinking about while listening to your talk on long horizon social interactions, or human-robot social interactions, that's an extremely low data regime, right? And we can't afford to buy a robot and then spend hours and hours interacting with it. So how do you think about this problem of like data compute versus algorithmic improvements? Yeah.
So I think I want to add to what Jitendra was saying. To solve long horizon problems, we have this very high dimensional sensory information that the robot is receiving. And then the issue comes that how do we process it to convert it into a representation, which is not only, but to convert it into a representation that the robot can use to solve the task. But in long horizon problems, the issue that is going to come is that as the robot is moving over this long period of time, that representation might need to adapt because the robot is getting new information, the human interacting with the robot is giving more information. So the thing, whenever I see the first issue comes on the part on how can we reduce this high dimensional data into this abstracted structure, which is feasible for the robot and answers is able to resolve the issues or the problems that the agent needs to resolve. So the first question, the first part is this. The second part is that, cool, okay, now we have a representation, maybe it's adapting over time, but then the issue comes that how is the agent using this information? And here again, this is the algorithmic decision process that George talks about. And it needs to be efficient. If it's not efficient, like for example, if a human is asking a query, if we use brute force, and if it's taking like the whole overnight time to process that data, that's not good enough because the human would have moved on and would have a new query for the robot. So I think you need to handle both the cases where you process that high dimensional data into this representation, and then the algorithm, which is using this representation to answer or guide the human in any way, that is also efficient enough. So I think it's a two-way street, and just one thing might not resolve it. Does that help?
It makes a lot of sense. So it's not just a problem of data, it's not just a problem of algorithms, but we kind of need to improve both simultaneously. And I think that's a theme I'm hearing from all three of you.
There's one more thing I wanted to add. Something that Jitendra talked about was like all the algorithms that deep learning and computer vision are adding. So now in all the conferences, there's a plethora of algorithms. All of them are trying to solve these like high level goals. But one thing that I think fails is that they're making certain assumptions and treating that computer vision problem in isolation that works really well either in simulation. But once you start applying it into robotics, it fails because not all of the assumptions that they're making for that, they're isolated, like even the YOLO algorithm that I showed, like all of the assumptions they are making, they are not always going to be applicable in real robotics application. And that's why I think there needs to be a bridge between the perception and the robotics community if we need to move forward. So yeah.
Yeah, and that's why I get really inspired when I see the work that, both George and Jitendra were talking about, as well as yourself, which is really like building systems that learn from perceptual inputs, right? And that's where I don't see that many people nowadays working just on computer vision and kind of outputting a feature vector and saying, great job, right? And a lot of people are now working on the whole kind of thing together, both perception and decision making.
I mean, I want to make a personal remark here. I've spent, I don't know, I've been in AI for close to 40 years. And for a very long time, I mean, I've spent most of it in computer vision. And for a very long time, I sort of operated in this regime where, okay, we have these representations that we will produce, object, it says object category, it gives object pose. And after that, the robotics people should be able to take care of the rest. Okay, and I'm sure the robotics people operated on the assumption that, oh, if these vision people got their act together and they gave us X, Y, Z, we would all be in business, then the fault is theirs. And enough of this, right? So I think that actually the action and perception systems happen, they evolve. I spent a lot of time studying child development and stuff like that. And these systems develop in a very coordinated way. And so I think the classic divide actually doesn't make sense. So this is why for the last 3-4 years, I've essentially jumped into robotics, because I feel that if I want to criticize a field, I should do it from the inside rather than from the outside. Because from the outside, it's very easy to throw stones. It's only when you really try to solve the problems that you can understand things. So my observations come from this semi-outsider, semi-insider perspective. Robotics is harder than vision because instead of data sets, you need sort of simulation environments. And we can collect really good data sets now, but simulation environments are still not the real world. But I think the good news is they're getting much better. I think that for many tasks, they're getting quite good. Some of them they don't. The proof of the pudding finally is in the real world, but I think we should exploit simulation. At least I've changed my view on this. 5 years ago, I would have said simulation, who cares? This is not going to be real. I had the same attitude for simulation in vision settings where the data produced from graphics programs, but I've changed my mind. I think they're quite effective.
Thank you for that answer. I just want to do one more round of questions on a topic which I've been seeing people asking about, and then we'll call it a day for this panel. And this question is on uncertainty. So one of the themes I noticed in Ifra's talk toward the end was about uncertainty in task specification, but I noticed that there wasn't much discussion of uncertainty about the representations in either George's or Jitendra's talks. And personally, I feel that this is a really important, thing that we need to think about. We can't just assume that the skills we have or that the symbolic models we build are going to be accurate. We actually want to have some kind of notion of when they'll fail or why. How do you both, and maybe we can bring it to Ifra afterward, but how do you both think about, uncertainty in your respective work?
Maybe I'll start if that's okay. Yeah. So there's a couple of things. One thing is, I didn't show up there, but you can learn stochastic operators, and classical planning has had that for eons. But I think more importantly, what we found we had to do when we did the math that led to be able to learn those symbolic representations or those abstract representations from real robot data is we had to generalize that kind of notion of what a state abstraction meant. It used to mean a set of states in which the state abstraction in which you were in an abstract state. We had to generalize that to a distribution. And because we were able to generate that, and there's two types of distributions you can generalize it to. You can have a distribution of a states, or you can have a probabilistic classifier. Because we were able to generalize it that way, all of the machinery of probabilistic machine learning was kind of able to come in and help us kind of explicitly quantify how much uncertainty there is about what exactly the image of a skill looks like, or whether we can run a skill from a state. And that's sort of hidden at the top level, but at the bottom level, if something fails, you can kind of decide where the error was coming from and update the symbol in the right way. And you can also compute probabilistic answers about how likely in fact, that robot system was computing probabilistically the probability that a sequence of actions could be composed. So I think if we just adopt sort of fairly standard probabilistic reasoning all the way up and down the stack, and that involves changing what a proposition means. It's not a set anymore. We can handle those very naturally. I think classical planning land has very good probabilistic planners. RL and MDPs, all of these things have very good probabilistic planners. It's just a question of when you need to use that, or when you can just optimistically make a deterministic assumption, and then therefore get a much faster planner and run with it and see what happens. But I think we also just need to get comfortable with the fact that these abstractions at any level may fail. And then that's just part of life, right? Sometimes you make an abstraction, you plan, you arrive at the airport, you find out that it takes you longer to get from one terminal to the other than you thought, and therefore you miss your flight, and so you have to replan, and that's just a thing that happens. But it's the only way, actually, I think, to make effective long-range decision-making is to lean on these things, a bit more than we should.
Yeah, thank you for that answer. I mean, I think I hear two broad kind of ideas there. One is to build kind of probabilistic models or abstractions, and the other one is to sort of accept that the abstractions are going to fail no matter what we do, and kind of accommodate for that in our general algorithm in which we're using them. For Jitendra, on this question of uncertainty, I wanted to make it a little bit more specific. So one of the worries I have with kind of modular system like you described is in the boundaries between different parts of the system, right? So if you don't have a good notion of the uncertainty of each individual component, when you put them all together, what happens when one of them fails? Does it have kind of catastrophic results on the whole system? Right?
Fair enough. I think that I don't have anything very deep to say on this topic. I feel that I've invested a lot in how to make each skill work well, and how to make the interface between two skills work well. And this is, to me, like, okay, this is on the right path, and I don't know the final answer yet. And I strongly, I sort of like the control theory terminology on this a bit more. So I feel that rich sensing. I think that classically control theorists and roboticists have generally favored low dimensional perceptual input. And when they get high dimensional input, they want to convert it to low dimensional input as soon as possible. And I think that I'm not convinced by. I feel that the kind of compute we have and so forth means that we can actually handle high dimensional input like images and video, and let it go into the policy and use it that way. So that's my bias, that I think that we are making very good progress on that. So the use of visual data is no longer at this. So it's not like there's this abstraction of the pose of an object. But I don't think it's the extreme is, oh, you just take pixels and then you train from pixels to talks, always end to end. I don't believe in that either. I think it's something in between, and that in between is being discovered now as we are working on these problems. So that's that. On the fact that yes, every policy will have failures, and if everything is embedded as a control loop or as a policy, right? Then I think there's a way to recover from everything. So I have nothing to add, which is different from George.
Yeah, but I like the similar theme coming out for both of you, that it's okay if these things fail. We can make them more reliable, and we can kind of compensate for that. I'll just ask if you want to close it out by responding to these comments, and then we'll be done.
Yeah, I think I totally agree with that. Like whenever we are making abstraction, there's this implicit assumption that the abstractions might fail in the real world, and which is very true because robots even now, they're not able to open all the variety of doors that there are. We still need to make that happen. And with all the abstraction, they might not be even able to handle all the doors. So I agree that the abstractions that we are making are going to fail. And with the compute that we have, I think that we are going in the right direction, that at least we are trying to find the abstraction which is right for navigation or which is right for manipulation. As we get settled down that, okay, these are the abstractions which are these are the abstractions that we need to use for solving these problems, then maybe one thing that I think might be an improvement might be to adapt those abstraction. I think I'm a little bit like maybe biased, but I do think that the long horizon problem gives you the advantage that the robot is not just going to operate for just 10 seconds and just end, but it's going to have this continual sequential interaction. And that gives you an opportunity, for example, with one frame, if you're doing an object detector and the pose estimate of that object is not like accurate, but if you're getting these series of frames, you can use those series of frames to actually reduce the uncertainty. So I think that going in that direction is going to be very helpful, but again, it's computationally, it's going to take longer. So with the current compute, the direction we have is good, but in the future, I think that thinking on those lines on how we can use the adjacent frames or the adjacent information to improve the current information that we are having is going to help be very beneficial. And we definitely need to handle sources of uncertainty to make robust agents to solve these problems. So, yeah.
Thank you so much. Thank you so much, Efra. That was awesome. Yeah, we got a lot of different good answers for a lot of different questions that I asked, but I think overall I'm optimistic because there was a lot more agreement than I was thinking there would be. So yeah, let's thank all the panelists once again.
Thank you.
Thank you for having.
And we're going to transition right into, so you guys can go back to your seats. Thank you so much for coming. We're going to transition right into 5-minute spotlight talks. So this is just going to be a quick 20-minute session. So 4 talks, 5 minutes each. And then we're going to break for poster session and lunch. So let's see. For the first talk, we're going to have Chen Wang. Chen Wang, are you here? Is that you? Okay. Awesome. So yeah, we're just gonna, for the spotlight speakers, I'll give you a 1-minute warning up here. I'll be in the front row up here. Okay? Yeah. Your slides are all ready and you're gonna need this as well. Okay.
All right, so hey everyone, I'm Chen Wang coming from Stanford University. Today, I'm really glad to introduce our work, generalizable task planning through representation pre-training. So when we think about like future robots, people's home, that we really hope this robot can handle like plan for long horizon of tasks. And we also hope this robot can handle different kind of objects and in different kind of environments. So this really gives us a question like, how can we like teach the robot to generalize in these kind of situations? And one of the major challenges we found for recent work in task and motion planning is we found most of these tasks like focus on specific type of objects. So this gives us a question like, how could we like generalize these methods to new objects that are never seen before in the training process? So in this work, we propose our method called task planning based on pre-training representation. So there are mainly 2 major steps to achieve our idea. In the first step, we leverage a large-scale scene understanding data set and training a vision-based like object-centric representation to encode the semantic and geometric information of object into a low-dimensional feature embedding. And after training this pre-training representation, we further, based on it, learn a state transition model to modeling the robot skill effect. And so that during the test time, we can combine this transition model with a tree search algorithm to figure out a sequence of parameterized skills that can reach the given task goal. So to achieve this idea, we first collect the large-scale data set. By randomly sample the object from different categories into the simulated environment, we can generate a data set with different kind of object poses, and also objects with different kind of semantic state, like whether the food has been cooked or not. And after having this scene-level data set, we can train a simple vision-based encoder-decoder network and trying to reason the symbolic and geometric information of the object from its raw image inputs observation. And we encode this information into a low-dimensional feature embedding X. And however, only having this object level representation doesn't mean that we can have a good task plan. Also, the robot needs to know what kind of like a skill effect is going to happen after you apply a certain kind of motion. So most of prior work learned this type of like state transition model end to end, like from scratch, which usually like often overfitting to the training objects and environments. However, in this work, since we trained this transition model based on our pre-trained representation space, which has already been seen a lot of objects from the scene understanding data set, which has the potential to like summarize the common features of the object from the same category, so that this kind of representation would help this transition model to further generalize to new objects, even not included in the training set, but within the known categories. So more specifically, at each time step, our transition model taking the sampled skill and skill parameters as input and trying to predict the skill effect on the manipulated object. However, sometimes when changing the state of one object, it will also affect the others. For example, like suppose there is some food inside of a bowl, then moving the position of the bowl will also change the position of the food inside. So based on this finding, like we further use a multi-head attention layer, which is just a transformer encoder network, to reason the dependency between objects and output the final prediction of all object state in the next time step. By iteratively running this transition model, we can predict the skill effect for a long sequence of primary skills. And more importantly, because we want to make sure all these representations are always within the pre-trained space, so we later further use our pre-trained decoder networks and freeze their weights to train this transition model. After having this transition model, we can simply run a tree search algorithm by sampling the skill and the skill parameters and predicting this, checking whether the output the symbolic predicate the same as a given goal to see whether we have successfully find a task plan. We test our approach in 3 different kinds of tasks in our simulated environment called behavior. As you can see here, all of these tasks require multiple steps of interaction with the environment and really require the robot to reason the correct skill parameters that can achieve these task goals. So we first interested like how does our method perform when generalizing into unseen object. So we basically split our object data set into a training set and evaluation set, where all the objects in the evaluation set had never been seen before in the training process. And we found that the pre-trained representation act like a key for generalization. We found that those methods like end-to-end learn from scratch, like barely receive any kind of success rate. But while our approach with pre-trained representation can substantially largely improve the success cases. And in the second stage, we're also caring about how does pre-trained representation space perform in different kind of environments. So we change our kitchen environment into 3 different kind of layouts. And we find that our approach with pre-trained representation is way much more sample efficient compared with end-to-end learning from scratch, which only require half of the data sets to like quickly adapt to a new environment. So in summary, like in this work, we propose a generalizable planning representation that enables task planning for unseen objects. And this is also a unified framework for vision-based learning to plan on symbolic rich tasks. We have already released our code, including the training, testing, and data generation process. So if you are interested, like feel free to check out. Thanks.
Thank you so much. Next up, we have a pre-recorded spotlight from Mohammed Korer.
And I'm here to present our work on policy-guided lazy search with feedback for task and motion planning. I'd like to start with a motivating example. Say we want to deploy a robot arm in a chemistry lab. And we want to be able to specify high-level goals to the robot, like clean the beaker and place it on the table, or bring me a flask with 50 milliliters of water. And we'd like the robot to automatically figure out the sequence of steps it should take, as well as the actual physical motions it should perform in order to execute those steps safely. This is the problem of task and motion planning. And there's a long history of work going all the way back to the 70s. But one recent approach that we're going to build on in this work is PDDL stream. Now, PDDL stream defines a kind of formalism for posing these kinds of problems. So you can write your problem in the form of a domain file, which specifies the applicable actions and some routines for sampling satisfying motions, and a problem file, which specifies the initial state and the goal you'd like to achieve. You can then give these to a generic solver, which maybe thinks for a long time and then spits out a fully formed plan in terms of your high-level actions. Now, one of the really nice features of this approach is that the solver is domain independent, which means it'll work for any problem described in this formalism. So you can solve many different kinds of problems this way, using the same underlying solver. But if we care about the robot in the chemistry lab, we'll notice it's actually solving many very similar problems repeatedly. But yet these existing solvers kind of treat each of the problems independently and solve them entirely from scratch. So our main motivation for this paper is, can we design a PDDL stream solver that performs well if you haven't seen similar problems before, but can also be tuned to the specific distribution of problems that you might care about so that it improves from experience. And to that end, we propose a new solver for PDDL stream problems, which we call lazy. We show how a learned policy can be used to guide the solver such that it may improve from experience and lead to better performance on unseen test problems. Lazy performs a bi-level search, which gets progressively more geometrically informed as samples of possible motions are drawn during motion planning. The outer search seeks an action skeleton and is guided by a priority function f, while the inner search, which we call skeleton refinement, seeks to find the continuous quantities such as grasp poses and robot configurations that parameterize those actions. If refinement is successful, then the full trajectory is returned. But otherwise, we return to the outer search after having used the failures from refinement to update our search priority functions, and a new skeleton may be found on the next iteration. The priority function that we use to guide the outer tree search for a planned skeleton takes the form of a goal condition policy that we learn using behavior cloning on a set of training problems. In the expansion step in the tree search, the policy assigns a probability distribution to the applicable actions, indicating the policy's preference for taking each action from the given state. We encode the state as a graph where the vertices correspond to the objects in the problem, and the edges denote logical relations that they share. A graph neural network produces contextual embeddings for each of these objects, and a second GNN produces embeddings of the applicable actions, and finally assigns a probability score to each. This probability is then combined with an empirical estimate of the feasibility of each action to produce an updated priority score, which is then used to put these nodes back onto the search queue. Once a promising action skeleton has been found, we begin skeleton refinement. In this procedure, the streams belonging to each action parameter are evaluated, and feasibility statistics are maintained according to the success or failure of the sampling operation. These statistics are then saved into the database phi, which leads to updated node priorities in the next iteration. The search procedure underlying the outer search is a design decision, and we detail several different implementations and evaluate them empirically in the paper. We compare our approach to the best performing PDDL stream solver which does not use learning as a baseline, as well as a prior work which uses a graph neural network to order the creation of streams in a planning problem. We demonstrate a very significant improvement in solve rates and planning times across a range of manipulation problems using a 7 degree of freedom robot arm. All test problems are unseen during training, so the policy is able to generalize to new scenes consisting of different numbers of objects, initial placements, and goal conditions. We thank you for listening and invite you to check out our paper for additional results, details, and links to source code.
All right, let's thank the speaker. Next, we have Carl in person. Yes, so here's your mic. Here's your mic. I'll give you a 1 minute signal. Gosh, I'm going to see this quickly here. All right. Sorry? Presenter view. Do we have presenter view? No, it's not possible.
All right. I guess I'll just talk with the screen. Yeah. Hi, everyone. My name is Carl, and I'm from Carnegie Mellon University. Today, I'm going to talk about my project, planning with spatial temporal abstraction from point clouds for deformable object manipulation. So there are a couple of challenging challenges for sequential deformable object manipulation. The first one is you have to perform long horizon reasoning over the use of different tools. And the second is that since deformable object, it's very hard to model, we have to deal with the challenge, a high dimensional state of deformable objects. So we offer a 3-step approach to for this problem. So for training, we assume demonstration of primitive skills such as cut, push, and spread are available. And for testing, we would like our robot to reason and generalize to scenes with more entities and generalize to tasks with longer horizon. So the first step is to learn primitive skills from the demonstrations. We perform imitation learning with goal condition behavioral cloning to extract one policy per skill. And we use PointNet-based networks to parameterize our policy. And to chain the learned primitive skills together, we Okay, thanks. So to chain the learned skills together, we also learn spatial temporal abstraction on top of the scenes. So given a point cloud, we first decompose. Hello? Yeah, I think this is good. We first decompose the scenes. All right, thank you. Is it both of it? I think both are gone. Into different components, and then we separately encode them to obtain a latent set representation. This latent set representation allows to generalize to compositionally more components at test time. And then we train our temporal abstraction modules, namely a feasibility predictor, which is similar to the skill dynamics model that predicts, given 2 observations, can I go from one to another using a given skill? We also train a cost predictor to predict how close a certain observation is to the goal. And both feasibility predictor and the cost predictor are taking the latent set representation and are parameterized by permutation invariant networks. The final step is to plan over the skill abstractions. So given an observation and a goal, we map that into our latent set representations. And then given a skill skeleton, we use the trained feasibility and reward predictor, or the cost predictor, to compute a score for the trajectory. Since all the modules are differentiable, we backpropagate the gradients into the latent subgoals to update the latent subgoals. And then we enumerate all the skill skeletons and structures and pick the one with the highest score. So just to recap, first we learn short horizon skills, and then we learn neurospatial temporal abstractions to chain the skills together. And finally, given an observation and a goal, we perform latent skill space planning and output subgoals for in point cloud for execution. Quantitatively, our method outperforms all of the baselines, which includes an end-to-end RL method and a trajectory optimization method. And unsurprisingly, for generalization tasks where there are more components in the scene than in training, our method is the only one that achieves non-zero performance. And we transfer the planner to the real world because it takes in the point cloud observation. And we use parameterized skills in the real world to execute the task. So we kind of overlay the sub-goals on the top left, and we visualize the final target on the bottom left. And finally, we can visualize the plan generated by the planner in point cloud space. So in conclusion, we propose a 3-step solution to long horizon deformable object manipulation, and we can generalize to tasks with more entities and longer horizon. And here are my collaborators and sponsors. Thank you for listening.
Thank you so much. So yeah, because we're running late, we'll just do questions at the posters after this final spotlight talk. And I don't have the schedule with me, but yeah, it's one more pre-recorded talk by Yiming Lee and Arnav.
Hi,
Devnath.
everyone. Here we present our paper, Comparison of Model-Free and Model-Based Learning Informed Planning for Point Goal Navigation. This is joint work with Arnav Devnas, Gregory Stein, and Yana Koseka at George Mason University. In the point goal navigation task, a robot is deployed in a previously unseen environment and is required to navigate to a location within a limited number of steps. Here on the video below, we show a running example of navigating to the point goal with the frontier-based approach. A frontier is a boundary between free and unknown space, as denoted by the green pixels. Yellow pixels are the selected frontier. With the recent emergence of visually rich simulators and real-world environments, several learning-based approaches have been proposed. These learning-driven strategies are usually model-free, learned directly from images or intermediate representations in the form of an end-to-end architecture and trained via deep reinforcement learning. These policies are data-intensive to train, requiring billions of frames of training data. One of the example work is DDPPO. Another class of RL-based approaches adopts a hierarchical architecture. A high-level planner that predicts the waypoints on the map is approximated using a neural network and trained through deep RL. However, the waypoints may not be reachable. The example work is Devendra's active neural SLAM. Recently, Stein et al. Proposed a learning augmented model-based approach for point goal navigation. They introduced a high-level abstraction by assigning subgoals to frontiers and define high-level actions corresponding to traveling to the point goal via a subgoal. Under this high-level planning abstraction, a Bellman equation is used to represent the expected cost of executing a high-level action. To compute the expected cost for the first subgoal, the agent first accumulates the cost for traveling to the subgoal. Note that this motion occurs entirely in the explored area of the map, so we use A-star algorithm to calculate this cost. We use learning to estimate PS, the probability the agent will reach the point goal, and add RS, estimated cost for arriving at the goal location, or RE, estimated cost for having to turn back. After failing to reach the point goal via the first subgoal, the planner considers to reach the goal via the next subgoal. This continues until all subgoals are exhausted and the computation is recursive. In this work, we adapt learning over subgoal planner, LSP, to the visual navigation task. We develop a perception module involves building an occupancy map and a semantic map. Given an RGBD image, and the maps are obtained by projecting egocentric depths and semantic segmentation images to the ground.
We estimate 3 informative frontier properties from a partial map. Our model is a unit architecture where the input is an occupancy map, semantic map, and a goal map, where the goal map is a mask for the goal location. The frontier properties we estimate are PS, the probability that the frontier leads to the goal, RS, the expected cost of reaching the point goal via the frontier, and RE, the expected cost of failure, in that case, the cost of exploring beyond the frontier and coming back. The LSP unit planner knows how to avoid dead end. In the bottom row, we can see that the optimistic planner uses all of its limited time steps to explore frontiers that do not lead to the goal, whereas the LSP unit planner successfully reaches the goal through its learned frontier properties. LSP unit also achieves better performance than the optimistic planner by following closer to a shortest path, which is evident in the top row. Now, this is an example scenario. We can see that the LSP unit, through its learning, can avoid exploring rooms that do not lead to the goal and efficiently moves to the target location and thus achieves much better SPL score than the optimistic planner. LSP unit method outperforms the model-based optimistic planner and the model-free ANS approach, but is 7% worse than the state-of-the-art DDPPO method. But LSP unit needs around 230K data for training, whereas DDPPO was trained on around 2.5 billion frames. We can boost the performance of the LSP unit if we use an occupancy map with no errors. Some of the failure cases occur for LSP unit where the agent gets stuck in a narrow passage. In short, we adapt the LSP framework to use rich visual sensing and evaluate its performance on large-scale Matterport 3D indoor dataset with Habitat Simulator. We modify the learning module of LSP to learn properties of the frontiers from semantic maps, and we compare our approach with an optimistic planner, a state-of-the-art DDPPO, and a modular hierarchical reinforcement learning approach. Our experiment suggests that the model is comparable to DDPPO in point goal navigation in performance and requires much less training data. Another desirable property is that the representations used by our approach, example semantic map, are reusable for other navigation tasks. Thank you.
Right, let's thank all the speakers. Awesome, so this concludes the morning program. So we have posters outside until you get hungry. And we will be back after the conference events at 15:30 for afternoon program. Take care, everybody.
All right, hi, everybody. Welcome back to the workshop on learning perception and abstraction for long horizon planning. We're very excited to have our third panel of invited speakers. And to kick things off, we're going to have Rusba Motagi from FAIR and the University of Washington.
Okay, I'm going to talk about what's that?
Use this one.
Oh, okay, so I'm going to talk about embodied sequence representation learning. Recently, we have seen great success in representation learning in computer vision and NLP. For example, in computer vision, we have large data sets such as ImageNet, and we train our models using a supervised or self-supervised loss function, and we pre-train our models. We learn representations and we use them in different domains. Similarly, in NLP, they use a large amount of text, and they're training their models using simple self-supervised prediction tasks, like, for example, predicting the next word in a sentence. For the representation learning techniques in computer vision is not really useful for embodied AI. The reason is that they learn from the static images or videos, and the actions are kind of ignored in these settings. And similarly for NLP, they do not have a temporal dimension. While in embodied AI, we also have this temporal dimension that that causes like a sequence of basically we have a sequence of actions, observations, and so on. So here we are. So in this talk, I'm going to focus on one recent project. So we want a representation that's kind of universal, and we can perform different tasks, like such as word modeling, localization, and policy at the same time. So this is the architecture. So the output of our models, basically we have a unified architecture for multiple different tasks, like future frame prediction, pose prediction, predicting the pose of the agent, and also action prediction for a specific goal that's provided in that purple box on top. So that's our goal. So we want to learn the representation for the sequence of observations, actions, and poses. So what are the challenges? So embodied AI tasks usually have long horizon. So encoding those long sequences is challenging. Also, we need a common representation for observations, actions, and poses. And that's that adds to the challenges that we have for representation learning. And also, we want to train without any explicit task reward. So here's the architecture. So I'm going to explain what it does. So the bottom layer is the input. So we have the frames, the position of the robot, the actions that the robot takes, and there is this transformer layer on top that it has basically the spatial and temporal layers. So the spatial layer is responsible for learning the connection between different pieces of like one image. The temporal layer is responsible for aggregating information across time. So the supervision is kind of self-supervision. Our goal is to predict the next frame and so on. So I'm going to talk about that. So we have 3 loss functions. One of them is frame loss. So we want to predict the next frame in the sequence, and we use this recent techniques like VQ-GAN and that represent images by a set of code words, and they can get almost a lossless reconstruction of the image. So here we do that for next frame predictions. For example, this is a ground truth. On the left, you see the ground truth image. On the right, you see the reconstruction of our method. So we have action loss. So we want to make sure that we predict the action correctly. And also we have pose loss. So we want to be close to some a prediction of, to be close to where the agent is. Oops. Okay. So for training data, so we use a human trajectory that are collected in the habitat environment. So basically we record a sequence of RGB frames, actions, and poses. And we can do multiple different tasks at the same time. One of these tasks is future frame prediction. So we want to generate the future frame condition and the current frame and the actions. The other task that we are considering is point goal navigation. So how to move to a specific point in an environment. Like, for example, this is a top-down view of the environment. So we want to go from the orange point on top to the cyan point in the middle. We can also do object goal navigation. So navigate to an instance of a specific object category, for example, microwave in this case. And in addition to all these, our architecture can also localize the robot and provide like X, Y, Z, and X, Y, and rotation of the robot. So these are the results for these different tasks. The interesting observation was that, so for some of these tasks, like for example, for point goal navigation, using the 50x list data, we can obtain the comparable performance. And similarly for object goal navigation, using an order of magnitude less data, we can obtain like very similar performance to these strong baselines. Okay, so and these are some qualitative examples. So on the left, you see the seed frames, the frames that the robot sees. The top row is ground truth, what actually happens. The second row is one frame prediction. So we predict the future frame one step at a time. And the bottom row is 5 frame prediction. We predict like 5 frames into the future, and the actions are at the bottom of this figure. For example, the actions here are all of them are move ahead, and the method learns that the objects get bigger and bigger as we move towards them, and as you see here, the objects. The frames that we reconstruct has that property, and it scales up the objects. So, okay, so in summary, so we have a unified architecture for multiple tasks. We propose this spatial temporal transformer to handle long sequences, and also we used an order of magnitude less data compared to previous work to achieve the comparable performance. Yeah, thank you.
All right, thanks. In the interest of time, we're going to go right on to the next speaker. We're going to have Rusba come back for our panel discussion at the end. So for our next speaker, I'm pleased to introduce David Paulius. David is going to give us a blue sky talk. We asked for some blue sky early career visionary papers, and David's was one of the ones that we really enjoyed. So David, take it away.
All right. Hi, everyone. I'm David, or David's friend too. I'm going to give a talk today on my Blue Sky paper, which is entitled Object Level Planning and Abstraction. It's a pretty new idea, so bear with me. But I'd love any feedback if you have any. So so right now, we're like very privileged to have more capable hardware in robotics research. And we're very close to bringing these robots into human-centered environments, such as our homes. We still have a lot of challenges to tackle, though, until we get to that point. And one thing that we think about, and I do as well, is thinking about how we can get robots that can intelligently plan across long horizons, putting the name of the title workshop here, and also not only plan, but also autonomously operate over these dynamic spaces, and also just be able to handle new things that the robot would have never encountered before. So when we think about planning, we think about different levels or hierarchies of planning. So at the lowest level, we have motion level planning. I would say is motion planning. So you think about how does a robot navigate through free space. So it's about finding collision-free movements that allows the robot to be able to perform actions. On top of that is task planning or task level planning, where we have some kind of inherent structure about the tasks that the robot is able to do. And it's combining the motion planning part. So we have like trajectories, or maybe we have policies that are linked to these actions that the robot can do to solve some objective, higher level objective. So in this talk, I'm arguing that we should have another level of abstraction or planning on top of this called object level planning, which would allow a couple benefits actually that I'm going to talk about in the next few slides. The whole idea pretty much is we want to have something that is not specific to a single robot or environment. And I'll try to tell you why we should think about objects. So there are several motivations for object level plans. First off, object level plans, such as one right here, is an example of such a plan, which is a step-by-step instruction manual from WikiHow on how to wash dishes. So this plan is written in a very high-level manner that is closer to our understanding of actions as humans. So if you read it, if you could read it, pretty much it doesn't tell you anything about that's relevant to task and motion planning. So it doesn't tell you how you're supposed to go around in the world and pick up things or whatever. It just assumes like you have these actions as verbs that you just execute that action. And it doesn't also tell you about logical constraints about actions relevant to task planning. For example, before you pick up an object, your hands must be free. So, to pick up a bottle of the dish soap, you have to have an empty hand, a gripper. So it kind of works the same like with humans and robots alike. Like this tells you the bare minimum amount of information that you need to be able to execute this plan in any kitchen, any setting, new instances of objects, etc. So there are also other things that, because it's so high level, it makes them suitable for like just reasoning tasks. So for semantic, one thing is semantic reasoning. So perhaps you see words that are described as objects, nouns. So these nouns, they're just object types that you can reason over. So I kind of go into a little bit more of like applications of using semantic reasoning with my own work, but pretty much there's a lot of potential to be had with object level planning. So in this talk, I'm going to talk about my work related to an object level representation that I have been working with. So I propose that we should have some kind of interface between object level planning, the level, and also TAMP or task and motion planning level. So something should be there to facilitate this translation between very abstract high level concepts and task and motion planning level representation. So I had developed this knowledge graph representation called Foon. Disclaimer, this doesn't have to be the only object level representation that you should have, but we should just think about structures that represent things in this object level. And we can see here, let me see if I can. So that we have like nodes that represent objects. They have semantically meaningful names. And then we also have actions, which also have, they're closer to how we would describe things. So we think a lot of things about like picking, placing, pouring, just verbs that make sense to us, and they're very high level. So this isn't like as I said, it's not the de facto thing, but it's just something to kind of remember, like with reasoning over object types. So I'll go back to the motivations now. So there's like a lot of like benefits of using object level planning. So in this talk, I'll be focusing on these two aspects. So I argue that object level plans are portable. So they're written in a way that you could just go from one kitchen or one home to another, just like how we can just pick up a recipe and implement it our own way. And then I'll also talk about how we can make or facilitate planning and execution for robots. And I'll kind of talk about some other things just in the blue sky portion. So, oh, right, sorry. And then everything, of course, is going to be related to this object level representation, which I presented before. So first thing we're going to talk about is portability. So right here is another example of what I call an object level plan. It is a recipe for making scones. And as you can see here, it uses all these words for like objects and actions. And it tells you the bare minimum amount of information that you need. Like I said, it doesn't mention anything about the human or the robot. So everything is all just reasoning over object action. So there's no constraints. And you also benefit in the fact that you don't have to like specify a fixed way of having a robot to implement the effects of some kind of high level action. So I think that we should have robots that they should decide, like maybe in this instance, it should be able to perform picking and placing or some other action this way. And then maybe in another time period, it has to do it a different way. So we should be using these object level plans as a way to like give some domain knowledge, but not that the robot has to commit to that specific way of doing something. And so yeah, that just kind of talks about the point. So you have this like plan as a schema, which is portable. And then you use like other lower level forms of planning to fill in the gaps. So related to generalization, I mean, portability is generalization. So the idea is that we have object level plans that have words, and we can use words to like generalize. So like maybe we have a plan that is based on a certain set of objects. We want to find objects as words that are closer to those words that we know about, so that we can do really cool things with like natural language processing and semantic similarity. So here's just like a very quick example of something that I've explored. So like if you have an object level plan that specifies certain ingredients, maybe the robot doesn't have those ingredients. You want to be able to use something like some knowledge base to be able to decide are like two objects similar to one another. And if they are, then you could just swap out words in this high level plan without having to think about the task and motion planning part yet. So we kind of use this to this idea to be able to generate object level schemas for plans that we never encountered before. So we had this idea of using the trying to illustrate how we can generate object level plans for the recipe 1M plus data set using a very limited knowledge graph as reference. So we can select a recipe from recipe 1M. We have like a new set of ingredients. We try to find an object level plan in this graph that is closest to that. And then we can do very neat things with language, just replacing object names wherever needed. So this is like one of the cool things of just reasoning over object types, and rather than thinking about like instances at the moment. So more recently, I've tried to explore with some colleagues at the Technical University of Munich, trying to show how we can use object level representations to define task planning problem definitions in PDDL. And the motivation is that PDDL, sometimes it's not very intuitive, and also it's not designed to really be object-centric, because you can have multiple predicates to describe objects. And I think when we're thinking about things, we don't really think of them as like list of facts. We would think of them as just like object-oriented like entities. So the idea is to use an object level representation like Phoons to bootstrap this translation to task planning in PDDL, and then use that to perform manipulation planning. The advantage is that we can have one single object level plan, and we just use the, we decide upon runtime what is the specific way of performing the actions needed to replicate that object level plan. So here, the robot's supposed to be making a cocktail, Bloody Mary cocktail. And as you can see, objects are configured differently throughout the scene, but we were able to find a specific manipulation plan per scenario. And this is like the motivation for me, is that we have these object level plans, just like how we do it, right? We have like recipes, we can read them, but we will implement them differently at runtime. So, so now I'm going to go to the, I guess, some brief discussion on what I see could come out from this work. So I kind of talked about just some aspects like the portability and planning. There's still some other interesting questions that arise. So like with language, we've seen a lot of discussion about and a lot of talk about large language models and other existing models for like taking advantage of language. I think we can definitely use or think about how we can exploit them to create object level representations, or better yet, how do we even skip like an object level representation and go straight from language to like task and motion planning specifications. Not sure exactly how that looks like yet, but we'll see. And there would be other things to kind of think about as well. Just like how I showed with that one recipe, we can like derive things on runtime, how to do the execution. We can also think about the inverse, where maybe we want to build or learn object level representations, but you know, we have everything that's specified just for a single robot, single environment. So we have to think about generalization and compressing experiences that we learn from observation. Yeah, so many cool things, but I think, yeah, we should be thinking about abstraction and objects. So thank you very much. Love to hear any feedback if you have any.
Thank you so much, David. That was super cool work. For our next speaker, I'm excited to invite Kiana Esani from the Allen Institute for AI. Kiana is going to be joining us over Zoom.
Hi, can you hear me well?
Yes, we hear you well.
Okay, great. Hi, everyone. I'm Kiana. I'm a research scientist at the Allen Institute for AI, and today I'm going to talk about how we've been tackling the problem of long horizon planning using simulated environments. So there are two main reasons why we have decided to approach this problem from a learning perspective in simulation. First of all, the computer vision community has shown promising results for deep learning and generalizing to unseen visual domains. And second, the simulated environments can help us to scale the number of tasks and scenarios we are exposing our agents to. And as a result, we can train our agents much faster. So why do we think that long horizon planning is challenging? And I'm going to answer this question from a learning perspective. First problem is the sparsity of our rewards. As organizers mentioned, how can we train an agent when the goodness of that the agent's action may not be apparent, for hundreds or thousands of steps. This becomes especially important as we consider more complex tasks in and planning in more complicated environments. The second problem is the generalization gap. So even though that's one of the main reasons why we chose learning, the community right now is experiencing a huge gap between training scenes and evaluation in unseen environments. And the third problem is specialization gap. What I mean by this is you're expecting our models to perform long horizon planning in unknown environments without any calibration. The question is, can we help our models to plan better in specific target environments? So I'm going to start by talking about the sparsity problem. So I'm going to approach this problem for the task of object displacement, where the goal is to bring an object to a destination. For example, let's say the task is to bring the book to the bed. The agent needs to explore the room, find the book, pick it up, and then bring it to the destination. So how the community have been approaching these type category of problems is they've been tackling this from the object nav perspective, where the goal is to navigate to an instance of an object category. The problem here is that the reward is very sparse, so the training can be very slow. So the community came up with these approaches to make training much faster and much more efficient. The idea was, let's give the target location of basically, whether it's like the object or it's a manipulation problem, let's give the relative distance of the target in agent's coordinate frame to our agents. There are two problems with this. It's the task definition is unrealistic, and moreover, you're relying on these unrealistic sensors. Even though that's the case, it brings us a great benefit. The training will be very fast. The training will be efficient. So the question is, can I use the visual information to imitate these sensors so that in the absence of these sensors, we can still get those dense rewards for training our models efficiently? Here is the overall idea. So let's say that the target object is within the field of view of the agent. If I overlay the instant segmentation mask on the depth image and project it to 3D to get that point cloud, then I can calculate the relative distance and direction of the object's location in a camera coordinate frame. So then the problem basically reduces to having an agent that can explore very well in an environment, and as soon as it sees the object, it can calculate this distance and receive that dense reward. And you can see that basically, and before the agent sees the object, there's no compass or relative distance, but as soon as it sees it, we can get that relative distances. This brought us remarkable results in with only 20 million frames of training, which in the context of end-to-end training can be considered very fast and efficient. Great. So training is done efficiently. Are we done? Unfortunately, we are not. We are very far from that. There is a very big gap between how these models are performing in real world and during training versus how they perform in validation in those unseen environments. So there's a big generalization gap, basically. And these agents fail miserably when they are put in these unseen environments. So what is the problem? This brings me to my second point, generalization gap. This has nothing to do with making mistakes in long horizon planning. This is deep learning 101. We have a small set of 100 training scenes, and we are expecting it to generalize to novel, unseen environments. This is similar to training a model in SciFar and then expecting it to perform well on ImageNet. It's easy, right? Just let's scale these models. These models, we know they are data hungry. We should just provide more scenes and environments to them. Here's the problem. There are two general ways that these scenes have been generated in the community. There are either manually designed by artists and designers, or they are 3D static scans of houses. So the problem with this is it's time consuming and not scalable. It requires a lot of effort for each single one of these scenes that we want to add. The question is, can we find an automatic generation method that we can generate thousands and thousands of scenes with a variety of conditions? So here is where we introduced Proctor, which is the paper that won Outstanding Award at NURTS this year. And the idea is basically to sample random floor plans and lighting and objects, and basically procedurally generate a lot of scenes with a variety of different configurations. And you can see that this opens up an unlimited number of scenes with a variety of different conditions that we can train our models on. This can be like difference in the size of the environment, the objects that we are working with. And the benefits of training our models in these environments is that we were able to achieve state-of-the-art on 6 different tasks that all require long horizon planning. Many of these cases were even in a zero-shot setting, where we don't have access to any of the training data from the benchmark it is evaluated on. Proctor is very easy to use. Basically, just using these 4 lines of code, you can start using it in any projects that you wish. So I want to approach this problem from also a different perspective. This is my house. This is a video of my house. And for me as a customer, for these robots that are going to be used, like basically we're going to use these to build house robots. For me as a customer, I don't care how well it works on generalizing to different variety of scenes. I don't care how it works on a cafeteria or on a 6-bedroom mansion. My house is all I care about, and I want my robot to be specialized in my apartment and not anywhere else. So this brings me to my final point, which is the specialization gap. The idea is, if I can get just using my phone and a quick scan, just a video that you watch, a quick scan of the environment, if I can get a template for my environment, and it doesn't need to have any details on any of the small objects, just having a rough 3D bounding box of big objects is enough. Then I can procedurally generate the variants of these scenes. So we are actually doing this. Just using an iPhone, we scan this environment, get the template, and then procedurally generate these variants. And then we can train our models in simulation in those specific environments. And surprisingly, when we deploy these in real world, they work perfectly, just off the shelf, no sim to real adaptation is needed. So again, with this video that you watched, this is the layout that we get. And as you can see, there are many objects in my house that were not scanned. And the variations of this environment out of my house is very different from what my house looks like. However, because we are training these models on a variety of different scenes with different abstractions, different clutters, different object types, different lightings of the day, our models are able to achieve very good results with just a very simple architecture, no mapping involved, just using RGB. They can localize themselves, the agents can localize themselves and basically just navigate to the target object that we have in mind. Great. So what we did was we took these models, took a model that is pre-trained on Proctor, fine-tuned it on these specific environments that we were interested in, using just a few millions of fine-tuning, and evaluate them in these diverse set of scenes. And this is how Proctor compares with our model, and the results are remarkable. We are achieving more than, on average, more than 70% on the task of object nav, which is something that we've not seen before in the learning community, especially in an end-to-end training method. One very interesting observation was that our models were way more robust to our baselines. They're robust to people moving around, to clutter being present, and even if you rearrange the furnitures, the big furnitures which were in this original scan, our models are still able to perform well compared to our baseline. And I want to thank my collaborators on all the works that I presented today. And I want to leave you with this final note that maybe long horizon planning is not as challenging as it used to be. And given all the frameworks and benchmarks that we have in the community, we might have been able to get closer to solving these tasks. Thank you.
Thank you so much, Kiana. I'd be really excited to use the phone to proc tool in my apartment. For our last speaker of this session, before we have the panel, I'm happy to introduce Dylan Hadfield-Manel from MIT. Dylan, take it away.
Thank you for the introduction, and thank you for the opportunity to be here. Let me just make sure that things are great. All right, so I'm going to try to be a little bit controversial today, and I'll also say that this talk represents some ideas that I've been thinking about and trying to figure out the right way to express for maybe 2 or 3 years or so. So first, there will be a bit of experimentation here. And second, I'm going to lean into the strong side of this because I want to make it interesting for all of you. All right, so I want to talk about how we can leverage planning architectures to design reliable robot systems. First off, my name is Dylan Hadfield-Manel. I run the algorithmic alignment group at MIT, and I get to work with all of these lovely faces day in, day out. Before I did that, I was a PhD student, and before that, I was a master's student. And there I worked on task and motion planning as my master's thesis. Here's me back in 2013, just finishing things up before I was about to move on to the next phase. Then I went to go and do my grad school research, and I kind of fell into the dark side, and that I moved away from doing task and motion planning. And I started looking at questions about how to specify tasks and goals for AI systems. And part of the motivation for that was because I spent a ton of time doing things like this, where here is some set of environments, and I would create a motion planning algorithm and tune it and tweak it to get it until it does what I want it to do in those environments. And then we go somewhere else and, oh, look, it does something that I definitely didn't want it to do. And who knows why it does something different there. It just has something to do with, in this case, we're optimizing a cost function that depends on distances from a bunch of target points you should avoid and some you should move towards. And, for some reason, it decides to go through the vase in this setting. I don't really know why. And this kind of unpredictability is super common. I expect that everyone in this room has had situations like this that you've fought against. Here's another example of a reward design gone wrong for an optimization system. So this is a deep RL system. It's supposed to be doing boat racing. It's clearly not doing that. But my question for all of you is, this is not a bug in the RL algorithm. I want you to tell me what goal it's optimizing. Yes, so it's going to be optimizing the score in this case. If you look in that bottom corner, you can see that number keeps going up. And what happened here is they didn't have access to the game internals. So they said, well, what we can do is we can OCR that bottom corner and tell the robot to optimize it. It works in some settings, but in this case, those balloons happen to be worth points. And if you spin around for circles infinitely, you get infinite score in effect. So this is a really ingenious policy, but definitely not what we wanted. This is actually a really well understood problem from economics. This is the problem of principal agent settings, where you have someone setting goals for someone else, and then they kind of cheat things. So there are numerous examples that exist of reward systems that are fouled up, and that behaviors which are rewarded are those which the rewarder is trying to discourage. I love this paper title because it's on the folly of rewarding A while hoping for B. You don't actually need to read the paper to get the main idea. Some other folks have taken this and applied it to problems of inequity in cases of prediction settings. And for me, I started studying this problem, and we had a paper in 2020 that I'm really proud of, where we proved that misalignment is unavoidable in some contexts. So here's our model of the world. We've got a true reward function R star, which is going to be in some high dimensional space. We have some proxy that's a low dimensional representation of that reward function that is much smaller than the overall one, and there's a shared resource constraint. So you could think of this as being something like if you're in a recommender system, your features are clicks, the engagement your system produces, the prevalence of hate speech, which is very complicated, and the community well-being. And you're supposed to balance all of these across shared resources that are things like user attention and space in the user feed. And we set up our basic model of this, and we saw something like this, where as you optimize, proxy utility goes up and true utility goes down. And it turns out I didn't cherry pick this setting. Actually, in this model, any fixed proxy objective will eventually lose utility. It relates to this kind of complex mathematical statement, and let me just go into that really quickly, which is to say that the sufficient conditions for any proxy objective that doesn't capture everything to be bad are just that you have decreasing marginal utility per resource allocated. So this just says you've got diminishing marginal returns in any one area of your problem. You've got additive constraints, additive separability for constraints and utility. This is kind of more of a technical condition. It's kind of like you can split things up into linear combinations for costs and rewards. And then you have non-zero resource use for everything. So you don't get anything for free is kind of the takeaway here. So this, I think, is a pretty strong result. And it basically tells me that optimizing against an objective and a monolithic big objective is something we should be wary of. Okay, so what can you do? Well, you might say, rather than a single reward function, let's have multiple reward functions. And then you go from this kind of setting where you're optimizing all of these at once, and you have to find a single set of weights that works for everything, to something more like this, where you can pick weights for individual problems and then generalize them into a single model. So turns out that people like that better, and they do a better job of actually producing good motion planning objectives when they do this. So the takeaway here is modular design is a way for us to approach this problem. And now that brings me to the elephant in the room, and this is where we get back into the real meat of today, which is talking about the fact that we're seeing this big push towards monolithic models. If you were here at the sponsor talk earlier, you would have seen this GIF, which is side note, this is a reason to prepare your talk at the last minute, because then you can get these recent results into them. But they were talking about, let's just try to get everything together into one big approach. And is this the future of robotics? Have all of us who've been working on modular designs of different systems been wasting our time? And I'm here to tell you that I don't think so. And I think that part of the reason is, imagine monolithic reward design at an industrial scale. Right? You're a company that's managing a robot that's going to go into people's homes, and all of it gets thrown into a giant data set that gets processed by tensor soup, and you don't know what things are going to break when, and when something breaks, you don't know whose decisions and what data they chose actually caused that problem. And we can look at other engineering systems and see something like this. So here's a blog post from Twitter in 2013. And what I want to point out is they have this quote in it that says, in our monolithic world, we either needed experts who understood the entire code base or clear owners at the module or class level. Teams constantly spent times going on archaeology digs to understand certain functionality, or we'd organize whale hunting expeditions to try to understand large-scale failures. I would argue that if we go the monolithic models route, this is where we're going to be as a field in 5 years. And that's not what I want to see. And the observation that drives this talk is that hierarchical planning representations facilitate modular design, and they enable failure tracking and modification, which is to say, we can have individuals who are responsible for different aspects of the code, different aspects of grasp or move or place or what have you. We can have people responsible for how that gets transferred into an implementation. And then you can trace failures to decisions. Now, I would argue that if you're building something in a high stakes setting like autonomous driving, that is a requirement from an ethical perspective and hopefully from a legal perspective. So here's kind of a rough idea of how we can try to apply that. This is from a paper in 2016 where we proposed a way to optimize for task plans. And the key thing here is we're thinking about tasks and primitives as encoding trajectory optimizations. So every single step involves some sort of minimization of a cost function subject to a set of preconditions that apply to the first step, a set of post conditions that apply to the final step, and a set of durative conditions that have to apply the whole time. And then we can do some things to try to optimize this. We use sequential quadratic programming. You could use something else. But notice that this is a specification of a really, really complicated reward function that involves discrete and continuous parameters. So what did we try to do next? Well, this is from a paper in 2021, where we took this idea of doing task and motion planning in this modular setting, and then we're just going to try to imitate it with machine learning. So to the extent that we have sort of machine learning in the system, it's just to try to meet that specification in a more efficient way than we could with a model. So some cool things that we had to do to make this work. We had a neat thing with feedback from the policy where you kind of project the rollouts of trajectories onto constraints. And we also had a hierarchical policy, and this is where the modular part comes in, where we both train first a policy at the high level to predict tasks, and then we train something at the low level to implement each one of those tasks given a set of parameters. And finally, we can select between those outputs, and that gives us our overall control policy. So you might start off with an initial state and a goal, then you kind of do your standard bit of planning, and this ends up with a task and motion plan. And what's nice is that if things fail, so here we've added in some new obstacles and we've got a failure where our robot's going to crash into an object. If that happens during execution, we can trace that out to, did the model fail at copying what the motion planner would do? Did the motion planner have constraints that were insufficient to guarantee safety? Did the task planner have an incorrect specification that it should have done a different action at this point in time? Or was the task module in the learn system incorrectly copying the task planner? And all of these are basically the 4 categories you can have, and you can have individuals responsible for each one of those to go yell at when things go wrong. I think this is something we need in our systems if they're going to go in high-risk applications. So in short, when we do this type of imitation setting, we can have geometric constraints on individual motions, and we can check those. We can have logical constraints on the composition of primitives, and then we have a clear supervised objective for machine learning. And this gives us a traceable system that supports accountability. If you want to try to build on top of this architecture, we've got our code up on GitHub. And I always tell people that no one's going to take away more than 2 things from your talk. So if you only remember 2 things from this talk, the first one is that reward design is hard and is going to place substantial constraints on our ability to engineer monolithic systems. And 2, hierarchical planning architectures facilitate the modular design of behaviors with attributable failure modes. And with that, I'm going to conclude the talk, and I'm looking forward to being on the panel for all of y'all.
Awesome. Thank you so much, Dylan. And so now I'd like to invite all the speakers to come up and join us for a panel. Oh yeah, we'll need one more chair. Thank you. Yeah. And is Kiana online as well? Okay.
Yes, I'm here. Can you hear me?
Mm-hmm. She logged off. Oh, okay.
So I'll check in with her.
Okay. All right, great. Oh. Okay, well, Kiana's joining, but maybe we can get started. Cool. So to kick things off, maybe we can start with what Dylan referred to as the elephant in the room. I'd be curious to just hear your thoughts about, ChatGPT, GPT-3, robotic transformers, as we heard from Vincent. Have these technologies prompted you to reconsider your own research agendas? What do you think the implications of these are for planning? Any just like reflections that you have from all of these advances that we've seen? Anyone can go first.
I guess maybe I can.
Oh, is your mic on? Yep.
I guess I can get us started on this. So for me, I think I've been, this hasn't really changed the direction of my research so much as focused and motivated it, seeing all of these things. I think what it points out is that there is the possibility to design systems that do meet this. Like my concern is almost the promise that these systems might work. I would I would feel a lot less nervous if we didn't have people who were itching to deploy large sort of tensor soup style systems into robotic settings, and thinking about self-driving cars or others. I think this really pushes us to need to make the case that modular, well-engineered systems that can match the types of safety constraints that we deal with in robotics. I think this sort of tells us, now is our time that we need to figure it out. And if we don't, things will move on, and then I worry that we'll end up with systems that have a huge amount of technical debt in the next 5-10 years.
So I just wanted to add as well. So I agree with Dylan that I think a modular approach is definitely better. I think some sort of inherent, like what I do like about these large language models that they've been able to do is they package a lot of domain knowledge into like this nice model. You could just prompt it, and you can get very basic things out of it that I think would be very good for like bootstrapping problems that we face. It's not necessarily to be like 100% correct, but I think it does give you something to like start with, and you could I think in the same degree of like my work, same vein, like I think you don't necessarily have to commit to like maybe plans or information that you get from these models, but you can use that just as a jumping point to figure out, okay, maybe this model is giving me something, like if I prompted it, how do I prepare this, like a recipe or assemble something or make something? You can then use that to, structure something, or like at least do some other forms of planning aside on the side with that. I do think that we shouldn't rely too heavily on them, because there's still a lot of things that we're trying to like understand about them. Like we don't really know, everything is like behind, like, just like Dylan said, just like with everything is like tensor based. There's like just a bunch of like numbers, and we don't fully understand like how things are outputted. So I think we should modularize in the sense that we should delegate specific things that could afford to go wrong to using these models, and then maybe other things we can use more robust, definitely things that have tested the years, that have stood the test of time. We can rely on those things.
Okay, I think the works that you mentioned are very influential. I think they have kind of revolutionized NLP, but our life is in embodied AI and robotics is much harder, because we cannot really easily go download a large amount of data and pre-train our models on those. So we are going in that direction. For example, the work that Kiana mentioned, Proctor and those types of things. So now allow those types of works allow us to scale and get lots of data, and so we can train our models. The other issue is that GPT-3 and the variants, so they are not really grounded in the real world. So yeah, they produce text, they're very good at that, but not really but not really grounded, and they are not really specific to a particular scene that they might provide some domain knowledge and say, okay, so this task can be done in this way, like for example, for I don't know, cooking omelet, you have to follow these steps, but those steps are not really specific to the current environment. So they can be, for example, I don't know, in the pan, my pan might be in the cabinet, and that general that language model has only like some general knowledge. It doesn't know that my pan is in the cabinet. So that so they are not really grounded in the real world, but in general, yeah, they have revolutionized the field, and probably we need something similar in embodied AI and robotics.
Awesome. So Kiana, I don't know if you heard the beginning of this, but we're talking about our.
No, I heard it.
Oh, okay, great. So soul searching about
Yeah.
GPT, and so far, I guess we've heard from Dylan that he's a little worried that they might work, but issues of reward misalignment could really crop up if we just have these large monolithic models. So modularity is going to be super important. I heard some agreement from David on that, but also some optimism about whether we could sort of use these as a repository of common sense knowledge and maybe one module among many modules in designing robotic systems. And from Ruzba, it sounds like he would also agree, but sort of focused on the challenge of generating data and dealing with specifically embodied agents. Yeah, what are your thoughts?
Yeah, so I think I have a slightly different opinion from the other panelists. I actually think it brings a lot of opportunities for us. So far, in terms of the reasoning that we're doing in the embodied AI task, we are very limited to some very basic judgments that even maybe like a 2-year-old can do, whereas these models are bringing a lot of more complex reasonings. I agree with Ruzbeh that they don't have the grounding in the real world. So they don't have even like the visual grounding is something that is still like the connection is not there. But I don't think we should just dismiss these models just because of that. The level of tasks that we can perform with these, and we have already seen a lot of progress in the robotics community. I think I attended the workshop, a 4-hour workshop in virtually in Berkeley the other day, and half of the workshop, 2 hours of the workshop, was the works of leading researchers, just showing how incorporating these models have enabled them to perform a variety of different complex tasks that we were not able to do beforehand. One argument for David, I think I don't agree with the test of time wait period, because I think that's one of the reasons why people, when AlexNet came out, they took some time to adapt to it. Sometimes we just need to trust or give it a try and see how well it performs.
Awesome. Yeah, so one of the things we want to do is have our panelists fight with each other because that's more fun for everyone. So you raised some provocative points, I thought. Does anybody want to respond to that?
I guess I can sort of jump in. I think there's lots of value in these models that we can use. My point is not to say that we shouldn't pay attention to them. I don't want to be the person who's saying ignore AlexNet in 2012 and 2013. And I hope I'm not doing the same thing now. I think my concern is the promise of like, if we look at the large language models and the attempts, like the recent like Galactica release and sort of all the things that happened there's kind of this idea that because we can generate all this text, that we can figure out how to make it do what we want afterwards. And I think that's something we should study as much as we can. And in fact, that's something that I do work on in a language setting. But I think in robotics in particular, if we can't trace design decisions to failures, I'm really worried about building those systems. And I worry that the current push is driven by more of a goal to build AGI than it is to build systems that work well.
Makes sense to me. Does anybody want to respond to that, or we can move on to another topic?
Yeah,
Great.
makes
Okay.
sense. Yeah.
So another kind of big picture question is, what do you think the role for planning will be in 10 years in robotics? And so feel free to answer this in like a very broad way. You can define planning, or you can have a narrow definition like we've heard about task planning, motion planning, and so on. So do you think, yeah, just where do you think planning will be in the conversation in the robotics community at CoRL 2032 or whatever?
We can start from the online panelists.
Throwing me under the bus, Ruth. Um, it's a hard question for me to answer because I'm not from the planning community. And it's hard for me to say where I think it will go because I think a lot of the hand design modules that currently exist, these can be automated. And I think basically we can leverage the language to make these reasonings that you're hand designing. But where exactly we will be in terms of planning, I will leave it for more senior people in the panel. Here, Rusbe, you go now.
I think it's hard. It's really hard to predict. I mean, people. I mean, big people made a lot of wrong predictions like 10 years ago, but I think it's probably planning will not exist in 10 years. So we should have probably everything will converge towards a unified model that does everything. Like it does planning, it does localization, it does it learns about the world and so on and so forth. So I think probably we will have a unified model. So that might be against what Dylan said, like we cannot really trace back the failures, but maybe in 10 years we will go towards like unified architecture. So planning by itself might not, I mean, it's part of that, but probably by itself does not exist, will not exist as a separate entity.
Great. That's exactly the kind of spicy answer I was hoping to get. So let's hear a response from a planning researcher.
I guess that's me right now. So I guess what I'll say is, as a prediction of what will happen, I don't know that I disagree. I certainly don't hope that's where we end up. I think a vision for a world where planning is still an integral part of the specification of systems makes a lot of sense. I want to be able to understand, at least in some sort of interpretable abstraction, when my model might choose to do certain kinds of things. I want to be able to do things like, think about the difference between trying to do programming via specification, where you specify a set of constraints that you then have something else that optimizes against those constraints and verifies that those constraints are in place, versus what it looks like using Codex or ChatGPT to write code for you. You write down a set of specifications, you get something out. It may match what you want, it may not match what you want, but actually verifying that is really, really challenging, and it's very hard to trace back what went wrong. And so the people I know in PL are really, really worried about the impacts that this will have on software engineering broadly. That this is, and this is a common story in human factors research, which is you build tools that are assistants, and then the atrophy that allows people to effectively kind of do things on their own, the sort of knowledge that they had atrophies. So if you look at pilots today are much worse than they used to be. They're just nowhere near the level of skill that they used to have. And it's because we've got all these great systems that automate things around them. And, that there's been a lot of attention paid to that. And looking at kind of the rollout of Codex and things like that, I don't see us learning those lessons. And so I worry that, not that it's not going to work from the get-go, but I worry that in 5 years, we will be really, really stuck. And so the vision for how things can succeed is kind of the role that you might have with those constraints that you would verify in a program induction setting. Planning serves as the grounding of the behavior we care about. And maybe we take all of the knowledge that we can and use that to learn more effectively, or to meet those specs better, or something like that. But planning to me is an understandable specification of behavior. And I think we shouldn't neglect the importance of that.
So I have a quick follow-up question that I want to hear from David as well. So I know in AI safety, people talk about an alignment tax, which is like the cost that we would have to pay to make sure that our agents are aligned versus like just directly optimizing our objective. Do you think that planning is like kind of an alignment tax, or maybe not an alignment tax, but are we just paying a tax by doing planning research to ensure that our we can debug easier, or do you think there's virtue in planning in itself?
Short answer, yes. Slightly longer answer. It's a tax that exists for, like, I think actually we will get a payoff from that down the road. Like it's not something we'll just be paying a tax on forever and never see value from. This may prevent us from doing certain kinds of things. It may be harder, but I think that this cost to understand our systems is very much worth paying at this point, and probably worth paying in perpetuity.
So it's worth it for the long term. So we avoid a local minima as a community.
Yeah, and I also, I would say this applies to the development of AI systems really broadly, that we should focus on building things that work and solving the problems that real systems have. And I think it's just hard to imagine a practical sort of industry scale engineering organization centered around a product that has one monolithic model at the center of it.
Bruce, are you getting ready to respond?
So, yeah, I think I'm gathering my thoughts. So before, yes, so it makes our life easier in debug and so on. But I think at some point we will lose our capability to really understand what these models do. Like, for example, before deep learning getting popular again, like back in the like SVM era, like, so we wrote down rules. We knew like what objectives we were optimizing, and everything was clear. If something went wrong, we could go back and modify our objective and so on. So that was very good. So we could really debug our systems. But when deep learning became popular, so we lost that ability. So we could never. It was just a black box. We gave it some input, we got some output, and we didn't really understand what was going on. I'm not saying that this is a good thing, but sometimes we have to for better performance, we might end up losing this interpretability. And it's again, I'm saying that, don't get me wrong. So I'm not saying that this is a good thing, but it might happen. It might happen naturally.
Okay, so this is fun. David, with you sitting in between this fight, could you weigh in? What are your thoughts?
Okay, I think everyone made pretty good points, to be honest. I think that we're going towards that vision that Roosevelt just said, like, we're probably gonna get more like, monolithic models and stuff, systems that we could just see everyone's going crazy for that right now. We're gonna be pushing for that. I still feel like I have a bigger appreciation for planning still, because I think there are just certain things that we still need to verify. I feel like I'm totally fine with like delegating certain parts of, like, maybe the whole loop of execution planning with the robot. I'm trying to delegate certain parts to like these new approaches, like like Roosevelt said, for example, we're now doing a lot of things with deep learning, and they do very good things with like perception, language generation, and so on. I think those things we can definitely, like, I without a doubt, I don't really would care too much to like go into it. There might be some other parts for like maybe other fields that might care about that, but those things I'm okay with, like, not having to like formally verify. But there are some other things with decision making, it could be very important, like I don't know, in certain cases, like maybe for me, if I had a robot like in the home and it does something wrong, then I wouldn't be like super upset. I'll just try to do it myself or correct it. But in a situation where you don't really have, like it's not as flexible. Like maybe you have like in an assistive care setting or something. You need to have that kind of confidence that this whatever systems you have in place, you have like you could rely upon that. Maybe you could like trace how it comes to making a certain plan or decision. Maybe it does something wrong, but you can like tune it and adjust it to like be able to correct it for something else, future actions that it has to take. So I think like, yeah, planning is still important to think about. At least some kind of structure is necessary. So that's why I think like at least you could, if you have this, this unified system, you should be able to like break it down still and put it back together again. So that's kind of like my take. Like I'm all for everything, but just I guess it depends on the application where the robots are being deployed. Yeah.
Makes a lot of sense. I have some follow-up questions, but I think Kiana might have raised her hand on Zoom. Did you want to jump in, Kiana?
Yeah, so I think I wanted to agree with Roosevelt a little bit, and then counterpoint with David a bit. But so first of all, I agree with Roosevelt that we might have to lose some of that explainability to gain some better performance. I think it's not the progress is not always linear or exponential, or it's not just always a rising curve. Sometimes we have to get out of the local minima first before we can get into that global minima. And I'm not saying that using these language models is helping with that in any way, but I think sometimes it's worth risking the performance that you're getting and the losing that explainability, basically. And I think the continuation of this comes to David's points that I absolutely agree. There are some tasks, there are some environments that we can afford making risks and making mistakes. So my Roomba can make as many mistakes as it wants, and I don't care if it's not efficient. If it does the job that I can do in 1 hour, in 4 hours, I'm okay with that. But if it's an autonomous driving, I need that guarantee, and I absolutely agree with that. So I think this is the beauty of research, that we can each work on different aspects of it. And there is value in both of that. And I think right now, if we had stick to that deterministic guarantee, we might not have been here in the computer vision as where we are right now. So I think we had to risk it and get 10% on ImageNet for a while and start like getting lower percentage on success rate and slowly build upon that to get to where we are right now, where if you want to get a guaranteed object detection, for example, the best method would be a deep learning method, like fully end-to-end model. But yeah, that's my take.
Makes sense. So I think a common theme that we're hearing is we're concerned about sort of end-to-end approaches, mostly due to sort of explainability, interpretability, safety reasons. So if that's the case, should we all focus our efforts on making these models explainable or developing new techniques for debugging GPT? Or would you instead sort of advocate for starting with something more structured and then sort of combining with the advances that we've seen in GPT, as Dylan has argued? Yeah.
Well, I think my answer is basically we should be doing both. I think, I'm here talking about planning. I also do interpretability work on trying to open up the black box of these big systems and get at what's causing their behavior and try to develop explainable and attributable versions of how you could assign responsibility to it. I do want to make a distinction between there's explainability and interpretability. The term that I used is accountability, and that doesn't necessarily mean interpretability, actually. What it means is when something goes wrong, I want to know who to blame. And I want that person to be in a position to fix the problem. And that's the property that I think we need. And I think you can try to design management systems like that for big systems that are mostly metric driven. Most of this involves lots of research on developing new metrics and having owners of metrics. And like, if you look at I talked about recommendation systems, because that's an area where I do some research on this. And the way that they manage those systems is they've got a giant suite of metrics, and every metric has an owner. And whenever you touch certain aspects of the system, you have to do A/B tests against those metrics. If they drop, you have to go by a certain percentage. You have to go and talk to the owner and accountability person on that metric and work with them in order to fix the problem, in order to get approval to launch the product change or what have you. And we should also be applying those in complex settings with large language models. We should be trying to make things interpretable and accountable. But I think I want to hit on one point about, we've talked about, sometimes you have to sacrifice explainability for performance. And a lot of times we don't question how good our performance measure is or whether it's real. We sort of know our performance measures are proxies, and we then acknowledge it and sort of pretend that they're true. So if you really trust your performance measure, by all means, get rid of the explainability, interpretability part. You still have accountability because you have that performance measure and you've got someone measuring it. But I think that we sort of need to be facilitating all of these approaches.
Does anybody else want to weigh in on this one?
Kiana, want to jump in, or?
I mean, yeah, sure. I think we are absolutely on the same page, and I agree with that. I think there will be some point in the research where we don't have performance nor explainability, and that's why we do open-ended research, in my opinion. And that's why we shouldn't all be doing super open-ended research, and we should have the planning community continue the efforts in that area. We should have explainability, interpretability work, continue working on that. We should even have the more people on the more theoretical side doing the guarantee proofs, and on the other side, I think we should also be open to trying out things that will be working with a black box that maybe later on we'll find how to interpret those. Maybe later on we'll get a better performance out of it. But I just think it would be good to leave that door also open to lose everything for the chance of maybe getting way better performances down the road.
Makes sense. So I think we're running a little short on time. So I'll ask one final question. I'm going to really put you on the spot. So what's one thing that you heard from a fellow panelist today that really made you think that you're going to reflect on later?
Yeah, I can go ahead. Yeah, there's this issue of accountability. So I like that. So probably we need to do more research on that. So that's yeah, it doesn't unnecessarily mean like interpretability, explainability, but yeah, I like that idea in general.
I think I also like that term as well, because I think, yeah, that's true. If we deploy these systems, we should know like who to go to when something goes wrong, and we should be able to identify which part of, like when something failed, what was the component that failed, and then try to correct it as much as possible. I think also, well, I guess the first, I guess this discussion we had before too, 10 years along the line, we're going to be, losing to these large comprehensive systems. I think that eventually will, we're going to go to that point. But I think it's good to hear that, people are still, at least in the panel, we're still thinking about those small problems or different aspects that, we have to keep in mind while we're going to that vision. Because I think it's wonderful to have, there's beauty and simplicity and elegance. I think that having something that does everything is kind of cool, but I think at the same time we have to put in that work, and it sounds like everyone's on the same page with that. So that's what I'll say.
I think for me, I'll be thinking about the sort of clear split between issues of generalizability and specialization. I think that kind of combined with ideas around procedural generation for environments fits really nicely with training models that we understand what they're supposed to be doing. And I really appreciated that distinction and abstraction. I think that's a really powerful one.
I think I really also, I agree with Rusba and David that accountability was an interesting topic that we talk about it less often, and we probably should, especially after we start deploying these models in real robots. One other thing that I want to mention is there's always this fight between the robot assistant computer vision people or the planning community and the learning community. And I think if I want to take one outcome, because we learned today that you take one or two takeaways, my takeaway is we should do both. And instead of just trying to criticize the different directions, we can just sit in one panel together and learn from each other. And basically, there will be a lot of communication that can be done to improve both sides of the perspective.
That was a perfect note to end on. So thanks again to the panelists. And so with that, we're going to move right into our final spotlight talks. First up, we have Edward Hu. Is Edward here? Great. We're going to use this. No, we're just.
Hi, everybody. I'm Edward. I'm going to be presenting our work, Planning Goals for Exploration. This is joint work with Richard Chang, Oleg Rybkin, and Dinesh Jayaraman. So let's first start out with the setting of unsupervised task discovery. In this, we drop an agent into an unknown environment. So maybe we drop a household robot into this new kitchen that's never seen before. First, we run something called the exploration phase, where the robot figures out what can be done in the environment and how to do it. Then in the evaluation phase, we set arbitrary new tasks in the environment. So we may ask the robot to first, play with the tools like the utensils, open some drawers. And then the next day, we ask it to clean up the kitchen counter. So in this setup, it's clear that the more diverse exploration experience the robot gathers in the initial exploration phase, the wider variety of skills it can learn from that data set, and in general, become a more generalist agent, right? So let's talk about task discovery and goal conditioned RL. In goal conditioned RL, we train an agent policy conditioned not just on the state, but also a goal variable G to reach any specified goal state G. And in goal conditioned RL, what we typically do is do something called like go explore style exploration. And let me get into that. So pardon this formatting, but what we do is we set a goal G. So it's going to be like this goal star on the picture there. And we're going to execute the goal condition policy on that. And then the goal condition policy will reach some terminal state SFT. Then at that SFT, we're going to launch an exploration policy pi of E. And basically the exploration policy's job is try to seek novel states. We record this full trajectory in the data set D as an episode, and then we just run some like policy improvement, like using RL on this data set, and then we repeat this. It's clear that we should set diverse goals, like in this go explore style procedure, so that the agent can collect diverse data. But some, like some ill-posed questions is like, how do we reason about the reachability of these diverse goals, or like the plausibility, like how realistic are they? Like, how do we set diverse goals, right? So this is an open question that we aim to answer. How should an agent choose goals to maximize exploration? So our answer is we're going to do something like directly optimize for exploratory goals. So the key insight is we want to optimize for the exploration rewards gathered by our exploration policy pipe E when we choose goals. So to put that into a picture, we want to focus inside this red circle. So inside the red circle, we're going to try to just pay attention to the red circle, not actually look at the red circle as like a state boundary. But like inside this red circle, you notice that there's a goal star. And then we're going to try to pick a goal star such that when the goal condition policy is conditioned on that, it's going to reach some terminal state S of t. And then from that S of t, we're going to launch an exploration policy. And in terms of math, this is just like the objective here. And what the objective is saying is that we want to find a goal variable g such that the terminal state distribution of the goal condition policy conditioned on g lands up in a terminal state S of t such that the value function of the exploration policy thinks that S of t is high in exploration reward. So in order to do this, we need to predict where the goal condition policy will end up conditioned on some goal variable, right? And to do that, we can just learn a world model or a transition function. So we call our method planning exploratory goals, or PEG for short. And what we do is we start by sampling some goal candidates from the state space. This can be from the replay buffer or from the state space distribution if you have it. And what we do is we use the world model to predict how the goal condition policy will act conditioned on these goal candidates. So here we're going to inside the world model, so we're predicting the trajectory. We're going to condition the goal condition policy on this orange star, for example, roll it out, and then see where the terminal state is in that trajectory. Do the same thing for all of the goal candidates. And what we're going to do is we're going to score these goals by the exploration value of their terminal state. So zooming in on this purple goal star and then the resulting terminal state you get from conditioning on the policy on it, we score using this exploration value function. And what the exploration value function tells us is how well would the exploration policy do if it was rolled out from that terminal state, right? So in this case, it's good. We're going to do the same thing for that other terminal state with the orange goal, and we find that it's bad. So we just simply pick the best goal with this highest score for go explore exploration in the real world. So just zooming out a bit, this is a training loop of our agent. We start by generating a goal using that objective I just described. And then we feed that goal into the go explore exploration in the real world, roll it out, collect that episode in our replay buffer, and then just run policy improvement steps on that updated data set, right? So we're going to improve the world model, the policies, the value functions. And what's nice is that with this improved world model, like policies and value functions, our goal generation also becomes more accurate. So it's like a nice positive feedback loop. In our experiments, we test a variety of environments. We start with point maze. We also have continuous control, walker, ants, and mazes. And our most difficult environment is like this 3-block stacking environment, where we expect the robot to explore the environment thoroughly enough to discover block stacking like a 3-block tower from scratch, right? And basically, we're the blue curve. We do better than the baselines. We're the best in the hardest environment, which is the block stack. And focusing on the block stacking, first I'm showing you the evaluation of the goal condition policy trained on our exploration data. And I'm just showing you that the robot is able to actually stack the blocks, which means that our exploration was sufficient enough to find these interesting block stacking states. Next, I'm going to show you the exploration episodes during training time. So what is the agent actually doing? Note that the robot here is invisible. It's just represented by that yellow orb, but the robot's actually there. What it's doing is we're proposing goals that makes the goal condition policy stack the blocks into 3-block towers. And the reason why this is interesting is because naturally 3-block towers are great for the exploration policy to throw out the blocks. We find that throwing out the blocks actually is the best way to maximize exploration in this MDP. So in conclusion, we introduced PEG, an approach for goal setting to train goal condition RL agents to become generalists in a novel environment and with no supervision. And you can check out more results on our website. Thank you.
Thank you so much. We're going to jump right into the next talk. So next we have Shuo Cheng, who's going to tell us about guided scale learning and abstraction for long horizon manipulation, and that'll be virtual.
Tasks and
We present our work guided skill learning and abstraction for long horizon manipulation. Our motivation is that different tasks and domains may require reusing similar skills. So we ask the question, for long horizon tasks, how can we learn all skills efficiently and make them reusable for new goals and domains? We propose LEAG, Learning and Abstraction with Guidance. We developed a framework that progressively learns skills by integrating task planning and skill learning. We leverage the state and action abstractions to efficiently learn reusable skills, and we show that our learned skills can generalize to new goals and domains. Our framework starts with a group of defined symbolic operators and a library of randomly initialized skill policies. Given a task goal, we generate symbolic task plan to invoke corresponding skill policies for execution. The failed skills will be recorded for further exploration and learning. To improve the failed skills, we leverage symbolic operators to extract the state of target objects and use the desired effects to generate the reward, yielding a skill-relevant state space and an operator-guided reward function. The improved skills will be automatically integrated into the framework for accelerating the learning of new skills. This process is repeated until all the necessary skills are mastered and the task is solved. Our learned skills support reuse across task goals and domains. To gain more understanding of the learning process, we use the hammer place task as an example. The goal is to place 2 hammers into 2 cabinets. The robot must first learn how to open the cabinet, then it can learn how to place objects and close the cabinet. We plot the executed skills in each iteration, where the y-axis denotes the proficiency. Our framework will continuously improve all necessary skills in a sequential way until finally the task is solved. Now let's see some video demos. For the plug-in hole task, the robot needs to insert the 2 pegs into the 2 holes, which requires long-term reasoning and context-rich manipulation. We also show that our learned skills can be directly reused to solve new task goals. For the hammer place domain, since the workspace is tight, the robot must first close the open cabinet, then it can try to open the next cabinet, which requires complicated reasoning. We also show that our learned skills can generalize to new task goals. For the make coffee task, the robot needs to open the cabinet, pick up the pot, insert the pot into the machine, and then close the lid. We show that our learned skills can be reused in new domain to facilitate the learning of new skills. Lastly, we show the real-world execution of our learned skills on Frank Panda robots. To summarize the work, LEAG allows continuous and efficient extending its skill set through integrating symbolic planning and skill learning. LEAG is effective at solving long horizon tasks and generalizing the learned skills to new goals and domains. For more details, please check our webpage and paper. Thank you for watching.
All right, excellent. Thank you, Shuo. So next up, we have Shreth Tooley in person. Awesome. And we'll be hearing about learning generalizable task policies for embodied agents in domains with rich inter-object interactions. So this first slide. Yeah.
Hi, everyone. I'm Shrestha, and today I'll be talking about our work titled Learning Generalizable Task Policies for Embodied Agents in Domains with Rich Inter-Object Interactions. This is a joint work with Mustafa, Mosam, and Rohan Paul at Indian Institute of Technology, Delhi. So we all know that task planning is hard, especially where there are complex symbolic interactions possible in a world domain. For example, as you can see on the right, there is a mobile manipulating agent that is told to perform high-level tasks such as cleaning a particular room in a household, or another agent that has been told to fetch or transport objects in a factory-like domain. And these are complex or challenging specifically because of the rich inter-object interactions that are possible in such environments, for example, containment, attachment, and so on. And we might have to sequence several tasks or several plans one after the another. So these might include transport, fetching, etc. And this requires some sort of common sense generalization to be able to generate goal-reaching plans in unseen domains where there are new words, new objects, new interactions possible, which possibly it can be done through common sense knowledge that humans innately possess. So from that motivation, we hypothesize that human demonstrations of tasks with existing common sense knowledge corpora can help us generalize to novel scenes, objects, and interactions. Specifically, we have this technical approach where we develop a novel imitation learning model that extracts this common sense knowledge purely from human demonstrations of goal-reaching symbolic plans. More formally, we want to learn a policy pi that takes as an input the current state, the symbolic goal predicates that you want to achieve, and some sort of a history of the actions that have been performed or executed. And we want to generate an action to be performed at that particular time step. We realize this as a modular neural network model, which encodes this world as an object-centric graph, where the nodes correspond to objects and the edges correspond to relations. We perform independently semantic reasoning and metric reasoning on top of this world encoding, and we perform late fusion so that the downstream predictors can use them independently. And after that, we generate some sort of a goal condition attention, goal context, using the symbolic goals, which is a set of predicates, for instance, fruits in a fridge. And we also have some sort of temporal context that has been generated by this action history encoder that takes in the action history, for instance, the sequence of actions like pick apple. We use both this goal context and this temporal context to generate actions, for instance, place apple inside the box. We perform experiments on two different simulation domains. One is the spy bullet simulator, again, a symbolic simulator with Husky UR5 agent with a single manipulating arm. We have this virtual home unity-based simulator with a human-like agent with two arms for manipulation. We test various or calculate various metrics. I won't go into details, but we measure these different predicates that we established and compare them against the ground truth predicates that have been established by the human agent. And our results demonstrate that the proposed model is able to outperform baseline significantly in domains where there are not just for, say, new activities or new tasks that we need to perform, but also where there are random perturbations, for instance, where we perturb the positions of objects, where we replace tools with alternate tools that are possible, where we entirely change the goal predicates. And even then, the model is able to outperform the baseline. This is a sample rollout. For instance, here you can see that in the case of putting fruits in the cupboard, the model has not seen box at training time, and it has only seen, say, trays for transporting objects. But at test time, when there are no trays available, the model is able to predict the use of box to reach a goal state. Pardon the stuck video here. This is another plan where the model has not seen the use of glass for, say, drinking water and only bottles, but it is able to predict the use of water glass to be able to reach a goal state where there are no bottles available. And we also observe this graceful degradation over longer horizons, this performance drop where there are multiple manipulations, multiple actions required encompassing several objects. And specifically here, the goal condition attention in the proposed model allows us to focus on a small set of objects, pruning the planning space significantly and facilitating long-range reasoning. So final takeaways include that this is a key challenge of being able to generalize to unseen settings, where there is a rich space of object interactions, and we build a novel neural imitation learning model that extracts common sense knowledge to be able to outperform baselines in unseen and long horizon settings. All our code and data sets are available online. For our questions and technical details, please visit our poster. Thank you.
Awesome. Thank you so much. And last but not least, we have a virtual talk from Zhuxin Liang about sequence-based plan feasibility prediction for efficient task and motion planning.
Hi, I'm Yang. I'm here to talk about how to speed up task and motion planning with sequence-based plan feasibility prediction. If you ask a robot to rearrange the cabinets or clean and cook something for you, a lot of the actions would be actually to remove the obstacles out of the way, such as opening the door or moving the lid from the pot so that you can put the food in. Without such obstacles, task and motion planning will be fast. For example, on the tabletop, where the goal is to put the cabbage inside the pot, the task planner finds a plan such as pick and place, and the samplers will quickly find the continuous values that satisfy all the geometric constraints, such as collision-free paths, and that the final pose should be inside the region. But when there are articulated and movable obstacles, the task plan is infeasible because there doesn't exist any collision path to grasp the object. The second one is also infeasible because there doesn't exist any collision-free grasps to open the fridge door. Until 7 task plans later, we finally arrive at a feasible task plan, but the majority of planning time has been already spent on solving the unsolvable motion planning problems. With more articulated and movable obstacles, the planning becomes so expensive that an uninformed task and motion planner won't be able to solve it within timeout. Is there a way to skip all these infeasible task plans and directly work on the feasible ones? Instead of the iterative process between the samplers and the task planner to try out different task plans, we directly ask the diverse planner to come up with hundreds of possible candidate plans and sort them by incorporating information of the initial image and also the initial and goal literals in a sequence-based prediction network. And then we will attempt to refine the first plan in the order. If that doesn't work, we'll do the second one and so forth. Now, how do we incorporate all these different types of information and fuse the different types of modalities? Our proposal is to concatenate the sequence of actions in the plan and the set of goal and initial state literals in a big sequence. And in order to make the namesake PiggyNet, we're going to use images to represent the objects. Just kidding. We think images are important for incorporating geometric information to inform the task planner. So here's the framework. We first have a segmented image for each object or object parts to get the clip image features for each. Then for the continuous values, we'll make a one-hot encoding for their type and then put different digits of each value at different poses to indicate their type. And then in the end, we have several layers MLP to get value embedding of the same length and the object embedding. And then for the text, which are the names of predicates and actions, we rewrote them into proper English and get clip text embeddings for them. So after pre-processing, we will get each token for the transformer by averaging all the embeddings in each part of the sequence and add a positional embedding, which is type specific to the plan, goal, and initial state. We test the framework on the food rearrangement domain, where there are randomly positioned fridges, cabinets, food, and randomly positioned doors. The goal is to either pick up the object or move it to the table or another container. We compare the planning time of the diverse planner with or without PickyNet for plan feasibility ranking. We can see that from the result, PickyNet is able to cut down 80% of the planning time on those longer horizon problems involving both pick and place. And if we look at the number of false positive plans attempted before finding the correct plan, we can see that PickyNet is able to rank the feasible plans on top 3. And this dot size are in log scale. And we did something fun. We created another test set of problems where the goal is to rearrange staplers instead of food, which the models have never seen before. We see very similar performance gain using our PickyNet. So with plan feasibility prediction, we are able to make the previously unsolvable problems solvable. Thank you. I'm happy to answer any more questions during my poster session.
All right, and with that, so thank you, everybody. We have one more order of business. So, we reviewed a number of papers. There are 16 posters being presented here today and outside. And among those, despite, how everybody's submission was excellent and we really enjoyed them, there were a few that really stood out. And so we selected a few papers for consideration for best paper. And so here are the sort of finalists. So best paper runner-up number 1 was actually this recent talk, was sequence-based plan feasibility prediction for efficient task and motion planning by Zhutan Yang, and that was finalist number 1. We'll save all applause to the end. Finalist number 2 was guided skill learning and abstraction for long horizon manipulation from Shuo Cheng. And then the best paper award goes to policy guided lazy search with feedback for task and motion planning by Mohammed Kodir. So let's give a big round of applause to all the papers that really stood out. All right, and we will update the website to reflect these awards. So congratulations to all the authors, and thank you for everybody for attending today. With this, we're not done. We're wrapping up with the session in here. Just a reminder that the posters are out there and the papers are still online. So if you want to interact with the posters, I'm going outside. I have some things to say to some of the authors, some curiosity questions that have arisen since the last time I saw them, and also some questions for the panelists who are still milling about. But I want to just say on behalf of myself, Tom, Rohan, YZ, and Yana, thank you very much to the CoRL organizers and for all of you for participating and interacting today. So thank you very much, and I will see you out there for the next little while or so before we all head to the banquet later today. So thanks again. Have a good evening, and best of the rest of CoRL. So thanks a lot.